everyone? Alrighty. Usual checks. How are the captions? The ones that I promptly forgot. And sound and everything. How's everything? I don't touch the levels in between streams, but sometimes it seems like they change. Alright. Hello, Strawberry Jesus. Don't drink and derive, bro. Icy Yogi. Welcome. Hi, Hector HSC. We are just getting started here. So tonight, if you didn't know, is all about neural nets. So I'm extremely excited for this because I feel like this is what a lot of people wait for. And this is a lot of what people think about when they think about machine learning. And so I figured, we have to have a whole stream just to introduce the basics. So we're not going to be going into, variational autoencoders, super deep neural nets. I want to get the basics down tonight so that as we move forward and we talk about more complicated models, all of you have the tools to understand what is going on. So, first of all, last stream went really long. So I say, I hope I don't go as long this time, but I do have quite a bit to get through. Lots of interesting things. We're going to build our own neural net from scratch. So we're not using Keras, we're not using TensorFlow. We're going to do it ourselves, and we're going to learn from it. It's going to be an experience. We are ahead of the schedule. Are we? Do I even know my own schedule? It is January 2nd, Neural Nets 101, right? Yeah, okay, I've got it up here. January 2nd, Neural Nets 101. Okay. If we're going ahead of schedule, something has gone deeply wrong because it means that 1, I haven't updated any of my schedules, and 2, I forgot a stream. So it might sound like it's a good thing to be ahead of schedule, but for me, that would be not the greatest because that would mean I forgot a stream, which is probably, that's understandable. So thank you for checking at least. But hopefully we are on schedule. But like I was saying, last stream went quite a bit long. Reinforcement learning is a weakness of mine, and I really wanted to do it justice. But I realized it was a lot of content. So as always, the first little part of stream, I want to kind of recap a little bit, see if there are leftover questions. Reinforcement learning is such a novel, interesting approach to machine learning, and it's very, very different from the other kinds of machine learning that we were doing. So it is completely understandable if you watch that video and you're like, oh, I'm still feeling kind of shaky on some things. So now is a good time to ask questions about reinforcement learning. Like I said earlier, we're going to be doing neural nets tonight, so we'll do a little bit of a review of some terms that we learned from previous streams that we might use tonight. Hi, Onad, welcome, and hi, Algebra 97. Oh, hey, that is not a new textbook. Is that a new edition? Yes, this is an update to... okay, it's too far. It's over here. Hold on. I can reach it. That is an update to this textbook, which is great. It's a great, great, great textbook, but it is not new. That's going back down there. That's heavy. Takes up way too much room on my desk. And hi, the Kitty Slayer 7. Welcome. The textbook does not have a hole in it. It's my green screen. Okay, but so things we learned about last time. Agent, environment, reward function, value function. How do you all feel with that? Are there any leftover questions from reinforcement learning before we move forward into our wonderful, happy, it's time for neural nets stream? I'm excited for neural nets. I think that, oh gosh, I'm excited. I also think I might be a little bit biased because in a lot of ways I think they can be overrated. They can be. And I think people jump very quickly to using neural nets that they don't fully understand. And instead of trying some of our other cool models that we learned about. You know, we learned about some cool models, and that's always a good place to start. Red Hackett, don't you wound me like that. You say, yeah, we learned. I did my best, all right? I felt like it was... I tried, all right? And let's see. Icy Yogi asks, do you know of some usages of reinforcement learning when it comes to understanding noisy data like exoplanet detection? Yes, so you also reference a citizen science project, and I am going to hazard a guess that you are talking about a Zooniverse project, which actually one of my research mentors founded Zooniverse. He's very cool. And it was him and some other people, but I think he's really cool, so I'm going to credit him entirely. It was his brainchild, precisely because machine learning hasn't caught up to the level that we need it to in order to do those kinds of analyses. And so we have those citizen science projects in astrophysics because we need that labeled data. And so we need the human beings to step in and help us out a little bit. But reinforcement learning would not be my first approach, at least when dealing with that kind of data, right? Because I think some of the other approaches that we've learned and that I've showed you would be a better place to start. In particular, there's a lot of really cool neural nets that are wonderful for computer vision. So we will, I'm not going to spoil, as you can see. Yes, getting the direction right. Our last stream for this 12 Days of Machine Learning Miss will be on computer vision. And good. Okay, don't drink and drive, bro. You say reinforcement learning makes sense, at least in principle. That's good. I'm glad to hear that. And Onad, you missed, oh no, you missed last stream. It was a hefty stream. It was long, but I feel like it was really, really cool. It's really cool. I don't know. I'm biased. I love reinforcement learning. And let's see. XNRA, you say, what has the machine learned so far? Well, we will find out tonight. And virtual assistants. So you're talking about some old approaches. Well, you are in for a treat because one of the things that I wanted to open up the stream with, but really quick before we move on to neural nets, are we good? Are we good? Moving forward away from reinforcement learning. I said mentioned a few topics to read for a deeper dive. Dynamical systems theory, and what was the other one? Oh, it was like imperfectly known Markov decision processes, probably. And let's see, Luar Sombrio, thank you for following. Strawberry Jesus, I think you are in the Discord. If you remind me after stream, I will look up my notes from the previous stream and see what topics I had made a list of for people to look up. But yes, so we are good. We're ready to move on to neural nets. Well, we will return to reinforcement learning, as you can see from our schedule. We will return to it, actually, in 2 days, because Q networks are going to be a really cool approach applying neural nets to Q learning. And so we'll talk about that really interesting intersection of neural nets and reinforcement learning on Monday. And don't drink and drive, bro. You say it seems like reinforcement learning is a lot of linear algebra. Well, I think you could probably expand that and just say machine learning in general is going to be a lot of linear algebra. So, thank you, Scort1907, for following. And Casado Canjios, hi! You say, finally catching a stream early. I'm glad to see you. Welcome, welcome. And Diodev, welcome as well. Thank you for following. This is like intense holiday music. What is this? Am I just like uncultured? Waltz of the Flowers. Oh, Tchaikovsky. Okay. I was looking for some stuff that would kind of just hang out in the background. Some bells here or there. Something that would make us think of winter. This is very like, get excited. Neural nets. If you don't feel pumped now, I don't know how to help. All right. Yes, don't drink and drive, bro. You say that's reassuring because you love linear algebra. I'm so glad to hear that. I first did a lot of linear algebra in the context of quantum mechanics. So I have fond memories of linear algebra as well. Yes, it's good stuff. All right, so let's talk neural nets. What what is a neural net? Well, what's interesting, and you've probably heard this before, but still is a very fascinating thing to me, is that while reinforcement learning, in my humble opinion, reflects the process of human learning a little bit more accurately, I would say, neural nets are about the biological structures in our brains that learn things. And I'm not, I'm not a neurologist, so you're gonna have to bear with me a little bit here. But what is very interesting about this is that, machine learning engineers looked to the brain as inspiration for how to structure and how to create neural nets. And let's see, Kasado Kanhios, you say you read a Reddit post about sound canceling headsets and now you're traumatized? Oh no, I like my sound canceling headset. And Dioda, you say let's start. Yes, let's start. So, just like there are neurons connected in your brain, the neural nets that we're going to talk about tonight also contain neurons that will be connected. But here's a cool thing for you. I'm going to open up our session here with a trivia question. And those of you who Google, shame on you. Don't Google this. When was the first artificial neuron created? Guesses. I don't care. It's fine if you don't know, just guess. I think this is a really cool fact, though, and it's a wonderful way to start out. Okay, so we've got 1952, 1960, 41, 1970, lots of different things. All right. Let's see. Pro Leonardo da Vinci did it. When the first brain was evolutionized. 1706, 1957. I love these guesses. And Maddie Two Shoes, thank you for following. So let's get some specific numbers here. So if you can't claim a decade, but I will say that so far, Hector HSC, you are the closest because the first artificial neuron was created in 1943. Which some of you, okay, 2 billion BC, don't drink and drive, bro. I'm not touching that. But I think this is really a really interesting fact because when we think about neural nets, we think so modern. We think that this is the rise of machine learning. This is modern. It's got to have happened recently, right? Well, is this singing? Hold on. Would you like to know the title of this playlist, my friends? The title of this playlist is Instrumental Christmas Songs. Because I don't talk over... Oh no, this has vocals all the time? Okay. Well, that's not an instrumental playlist. We'll switch over to our golden oldies here. And Raiders! Hello! Carl 24K Data Science, what an excellent name. Welcome, Raiders. You have stumbled across the 12 days of machine learning, miss. Thank you for your raid. As you can see from our schedule, yes, I got the direction right. We are in day 8 of the 12 days of machine learning, miss, and tonight we're gonna do a soft but lengthy introduction to neural nets. And Nicole Janeway, hopefully that's for Captain Janeway, and Z Last Wolf, thank you for following. How was your stream, Carl 24K Data Science? Were you streaming data science? You would enjoy 365 days of machine learning. Well, virtual assistant, for example, tonight's stream, because I really wanted to show you how to build a neural network from scratch, and I wanted to really show you how to get all of these basic things down. It took me about 4 to 5 hours to prep for this. So, like I said in previous streams, I'm on PTO at least until Monday, so I'm on vacation from work. But when I go back to work, I'm not gonna have 4 to 5 hours during the day to prep all these streams for you. So we're gonna be going to once a week, math, maybe we'll make it math and machine learning Mondays. And that will give me enough time to prep, but I don't think I could do 365 days. I'm sorry. And let's see, Carl 24K, you say visiting from another data stream. Nice. Well, welcome. And so pip install for tonight, as long as you have the things that we've been using previously. So we're gonna use, scikit-learn, pandas, numpy, anything else? No, I think that's it. Yeah. It's not too much because we're literally going to do this from scratch. No, generic crew. No TensorFlow. Leave it, friend. Carl24K, thank you for following. Because really, we're going to build a crappy neural net tonight. It's not going to do well, but that's okay because it's kind of like, you know, the first time you try to make this fancy meal that maybe you had in a restaurant. You're like, you understand, even if you sucked at it, and even if it didn't taste very good, you understand a lot more of what went into making that meal. You understand the terms, you know, the techniques, the ingredients, even if, you know, it didn't taste so great. And maybe then next time when you buy it in a restaurant, you'll have more appreciation. So, tonight, we're gonna build a crappy but functional neural net from scratch. So the only thing you really need is NumPy for this. We'll be using our Titanic dataset because it was just easy. And we already know how to clean it. We're used to it. We know all the features. And so we'll be using that. And it'll be, it's going to be good. But again, the point here, unlike in previous streams where we were talking about, you know, hyperparameter tuning, regularization, ways that we could squeeze more functionality out of our machine learning models. Tonight, the point is going to be to understand more than to squeeze out good performance. In fact, our neural net's not going to do so great, but that's okay. We'll also talk about why it's not going to do great. Okay, chat, let me catch up on your questions. What are Street Maniac? You ask, what are the math prerequisites for this course? You have your baccalaureate in IT and you work as a Python dev. Well, welcome. We'll be doing Python tonight, so you should be well at home. I think so far I've managed to keep it to pretty much algebra. Tonight, fortunately, because I love calculus, but unfortunately, if you don't have a background in math, I will show you some calculus, but this isn't a calculus class. I will explain everything conceptually, and you're more than welcome to tune out the parts of the math that you won't understand. It won't be necessary to fully understand the math in order to understand the concepts. So really, like, even those of you who maybe Algebra 1 is kind of where you stopped and you know your variables and you know some multiplication and you're like, that's all I can really do. I want to keep this as accessible as possible. So we'll do some of the math for folks who love the math. But tonight my goal for all of you is that you understand the concepts most of all. And virtual assistant, you say making things easy takes talent. Thank you. I deeply appreciate that because especially tonight, like I said, I will show you the math, especially for those of you like me who are math nerds and you want to see it, but to simplify things without losing the richness of the content is quite difficult. And, you know, I feel like it's disrespectful to the intelligence of your audience if you kind of just water it down. So I don't want to water anything down for you, but I also don't want to lose the people who maybe they just like, I don't know, calculus was a long time ago for a lot of us. So don't worry about that. But your appreciation of the challenge of simplicity is very much welcome. I think one of the challenges that I've really run into in teaching some of this has been that people are like, oh, you must not know what you're talking about because you're not using the fancy, like, really long phrases that I've heard other people use. I'm like, because you don't need to. I'm going to explain the concepts, the approaches, the processes, without bogging you down in jargon and terms that will make you kind of just go, oh, this is awful. I'd rather play video games. So, but that doesn't mean I don't know what I'm talking about, trust me. Bathing Ape Supreme and PBA Coco, thank you for following. And Non-Dairy Neutrino, you say I don't need to flex, thank you. Well, you know, every time I do one of these streams, we get the haters, and that's fine. But I would rather appeal to the vast majority of people who haven't done calculus recently. So do not worry. And let's see. Last Miles, you say, well, you lost me. I never understood any of this. Oh no. Well, we haven't even started, so hopefully I haven't lost you yet. And Main Village Goat, you play video games, my friend. No worries. You have showed it. You've shown so much support for my stream. Don't you worry. And Goofy Lagrange, you asked, did you do a stream on getting started with loading the required packages? I did not. That could be maybe an add-on to the 12 Days of Machine Learning Myths, but so far this schedule that I have over here to the I'm gonna get this someday. That side is really all I've got time to do during my vacation. So, Mirzu9, thank you for following. Any last-minute questions before we move forward? Like I said, I know the reinforcement learning stream was a hefty stream, so don't feel bad if you didn't get all of it. We will do a small review at the start of next stream on Monday because we'll be doing neural nets applied to reinforcement learning. So what you learned last time and what you learned tonight, we're gonna smush them together and see what happens. So let me, while you all are thinking of your last minute questions, let me set up our beautiful Blackboard. And let's get, there we go. All right, yep. Blackboard's all set up. Crispy Creme, thank you for subscribing. Thank you. As I've told all of you in previous streams, the support really means so much because I did take some days off of my vacation. I needed some days to just be in my PJs and play some video games. But most of the days that I've had stream, I spend hours prepping for it, making sure the code runs, making sure you have good content, that everything runs. So your support means a lot. The appreciation, literally, this is why I like doing these streams, is because of all of you. So I greatly appreciate it. And Street Maniac, thank you for following. Donuts. No talking food. All right. So let's talk neural nets. And if you want to talk donuts, then I'm talking supermassive black holes. And then we're going to go down the rabbit hole of, tori and accretion disks. And that is not what tonight is all about. So, yay! Thank you, Street Maniac. You say you already bookmarked past broadcasts. And don't worry, if they're off Twitch, I'm archiving them on YouTube. So if you go on to Twitch and you're like, oh no, days 1 and 2 aren't there or something like that, have no fear. They will all be on YouTube as well. What are we doing tonight? Neural nets. That's right. What's happening? Is it broken? Nobody sees anything. No one sees anything. Hold on, please. I have an active pen. What on earth? Why won't you draw? Just this pen? Let's just reload that. That's never happened. Ever. Okay, hold on. I mean, this is like not a very great app. Shit, what is happening? Do I have to press like a button on my pen? Friends, we can't stream if we don't have a wonderful. Does anyone know what's happening? Hi Matt. Do I have the pen backwards? I do not. I'm writing. This one isn't one of the ones where you can erase with the back end of it. It doesn't seem to be the eraser. Let's just Is it possible a neural net is sabotaging me? I don't know, Stannis for King. Hold, please. My font color is not black. Why have you abandoned me, Microsoft Whiteboard? You've been my bae for forever. Who knows? All right. Well, you know what? You unplug it and you plug it back in and it works. So there we go. We're not gonna question it. We're not gonna, it's fine. Curly brackets. I don't even know if this app has layers. It's very simple. I picked it literally so that it wouldn't overwhelm me because I'm not like a Photoshop kind of, that's not my game. I don't do art. I do math. Not that the two are mutually exclusive, but at least for me. Yeah. And let's see, PJ Brazil turned it off and on. That's exactly what I did. Thank you, all of you, for staying with me through the panic. And thank you, Pratik. I miss my blue hair. I really do. But the fire department does not allow you to volunteer or work for them if you have funky colored hair. So, alas. All right. Let's get back to what we were doing, my friends. Neural nets. Excite. Okay. So, what did I just what did we just say? We learned that the first neural nets were, or the first neurons at least, were in the 1940s. So, what, you can't help if you have blue hair? Yes, PBA Coco. Unfortunately, yes, they have very strict uniform standards. So, alas. And Reaper of Pages, Matt, you say the platinum was your personal favorite. Well, you know what? Who knows? Maybe I'll go back to dyeing it. The pandemic has meant I'd have to do it from home, and that's also another skill I do not have is probably doing my own hair dyeing. So, all right. Let's okay. So what have we talked about? I've mentioned that they are inspired by real biological neural networks. That's right, you have a neural network in your brain. So, although there are many differences, of course, the inspiration, at least, are biological neurons and biological connections between those neurons are synapses in your brain. And Pixel Kitten 7, thank you for following. And you say, Matt, you say, I know this. Finally, a degree means something. Exactly. Okay, so like biological neurons, sort of, and Matt, correct me if I'm wrong. Like I said, I'm not a neurologist, but are artificial neurons. What are they going to do? They're going to receive an input. We're going to weight it in some way. We're going to sum it up. And then pass the sum through something we're going to call, pass the sum, let's see, to an activation function. Don't worry if you don't understand like some of the words, we're going to go through all of this. But the thing I want to focus on, and fret, thank you for following, is what does this look like? Right? Think back, I'm asking you, think back to elementary school maybe even. What does this process sound like? We're going to receive an input, we're going to do some mathematical operations to it, and we're going to have an output. And Euclid the Dark, thank you for following. No, it's not a black box. Oh, Nat, I'm banning that term. That term is banned. But you are entirely right with equation or function. All right, remember, and I think I actually drew one of these pictures in last stream. If you remember like the little like function box where like, you know, you have your x and it goes into the f of x and like you get your output like your y, right? Have you seen these? Hopefully some of you had seen them previously, okay? But yes, why some inputs? We will talk about that view style. Don't worry so much about the details just yet. But this should feel familiar. They're not super intimidating. They're little function boxes, all right? That's all we're going to be dealing with, but we want to call them something fancy because we want to feel cool about ourselves, so we'll call them neurons. But all this is, it's a function box, all right? So if you, later on when we've got complicated neural nets or the math is getting scary and you're like, God, neurons, just remember it's a function box. That's literally all it is. So the very first, what are you doing? None of that. Stay in your place. That doesn't at all look like letters, does it? There we go. like I mentioned earlier when I quizzed all of you when the first artificial neurons were created, it's 1943, or the 1940s. And they were called threshold logic units. Okay. So we got a couple different elements here in this word. We've got threshold and we've got logic. Units is just like, whatever. What does threshold make you think of? We've done some stuff with thresholds before. And I promise you, your first intuition about this, the last time I talked about thresholds, it's applicable here. So I know, brush the cobwebs off your brain from New Year's Eve or the, hungoverness, whatever it is. And recall back the last time we were able to talk about tuning a threshold, or we were interested in looking at what values met a threshold. Thank you, Master Darkweaver, for following. So Stannis, you're close. Severo, you are also close. You say separating the data into two groups. I see. So you're thinking about the decision trees. So the other thing, the last time we dealt with literally a threshold was actually when we were doing logistic regression, right? Because we said our logistic regression function literally said, if this input meets a certain threshold, kick out 1, otherwise kick out 0. And so we're going to be doing a very similar thing here. Willian Pikesau, thank you, Pikesau, thank you for following. And Boring Math Professor with the raid, with hopefully a math raid. Yes, let's swamp everybody with mathematicians, please. I don't know what Kummer's surfaces are. It's been a while. You'll have to be patient with me, friends. It's been a long time since I've had to do the complex math. I miss it so much though. And welcome all of you. Hi Raiders and hi Diatom's Attack. It's good to see you. I like your burgers, my friend. And yes, I love all of the emotes from your channel, all of the cool diatoms. Are they mostly diatoms? I recognize one of them because I recognize the leaf looking one because you were talking about that on one of your streams recently. But in any case, we have just started, so all of you have come at the perfect time. And we will be doing some of the math from neural nets tonight, but it's going to be a balanced mathematical approach because I want to make sure all the math nerds like me, we get our happiness from seeing the math, but then also we're not leaving folks behind. So we'll have a balance. The ones with mustaches are diatoms. Oh no, the leaf looking one isn't a diatom. I failed. Well, there you go. That's I'm not an expert in diatoms. Who knew? I really liked the one with all of the arches that you talked about. That was really, really cool looking. Just the symmetry was beautiful. Can we get a shout out, Loafbone, for Diatom's Attack and also for Boring Math Professor? Thank you so much, Boring Math Professor. You say, have a great stream. Machine learning. Yeah, so if those of you who are coming from the raid are really interested in machine learning, you want to learn more, the VODs for all of this will be on YouTube. The code and notes are on GitHub. So don't worry, even though we're on day 8 out of 12, you haven't missed anything. So you can very quickly catch up. And tonight we will be using some of the stuff we learned in previous streams, but if you get stuck, if you get lost, just panic and chat. I'll catch it and I'll help you out. And okay, well, Boring Math Professor, making dinner for your family before they starve sounds like a very admirable thing to do. So, and you said everybody in your chat was asking about machine learning. Okay, well then let me quickly give you all another look at the schedule. So those of you from the raid who are interested in machine learning, these are what we've talked about. So we've talked about linear regression, logistic regression. We've looked at several classification approaches. So I think we did decision trees and K nearest neighbors. Then we did an introduction to how to ensemble models, and we did that with random forests. We started some unsupervised learning with k-means and looked at the problem of unsupervised anomaly detection. And we had our introduction to reinforcement learning, which is my favorite. I'm still geeking. And tonight we're doing Neural Nets 101. So hopefully there's something there that that appeals to you. So, and Diatom's Attack, you do not need to watch days 1 through 11, also because we're on day 8. So days 9, 10, and 11 do not exist yet, my friend. But if you would like to, of course, days 1 through 7 are up on YouTube, and some of them are still up on Twitch, I think. And let's see. And thank you. You say this is incredible production value. Well, thank you. That means quite a bit. This is just a hobby for me. I'm not by any means like a professional streamer, so that means a lot. Thank you. I put a lot of work into this. So, and let's see. Thank you, Crow, for following. And Belganul, you ask, when is AI going to make your cushy software dev job obsolete? Oh, please, my friend. We're nowhere near there. Don't worry. Right now, hopefully machine learning will be a tool to help us be better at our jobs. I'm a big fan of something called human in the loop, which means we don't replace humans necessarily. We just use machine learning to augment and to provide more information for human decision making. And thank you for following Boring Math Professor. Go feed your family. Yeah, no worries. Like, please, food is important. Maddie Two Shoes, you say the effort I put in really shows. Oh yeah, no worries. You say it's 2 a.m. Please get some sleep. The VODs will be up, all right? Okay, so what are you talking about? Okay, so thresholds should remind you a little bit of what we were doing with logistic regression. That doesn't mean that all artificial neurons do logistic regression, but it's like, think back. This will be like our thought bubble, right? Because that's what they look like, right? Think back to logistic regression, right? And thank you for following Ilanarabiro? Sorry. Okay. And so essentially the way that these threshold logic units worked, and Snow Eye 19, thank you for following, is that we would have some input. Okay. Ah, too much green. Well, I love green, but let's change up the colors a little bit. Okay, we'd have an input, right? And that would get passed to our I'm bad at drawing. It's kind of even worse. All right. That would get passed to our TLU, our threshold logic unit. And this would, it would multiply our inputs by some weights. And then it would sum them. That's what we just talked about. And if that was greater than the threshold, it would spit out a 1. Otherwise, it would spit out a 0. This is very intuitive. Spawn! Hi! Thank you. Happy New Year. It's good to see you. It's always a special treat when you stop by and stream. And yeah, thank you, Diatom's Attack. Happy New Year. This is my sparkly New Year's Eve dress because I didn't stream on New Year's Eve. And MH Zanarium, hold on to your question for a little bit. I know you love asking the questions that jump miles ahead, but let's start at least for now with sums, because really what we're thinking about here, right? What is our input? We've talked about this before. This is our feature vector, right? And that might feel like a scary word. That might be like, oh God, this is one of those terms, but we've broken this down before. This isn't scary, right? All this is, these are our x's. Oh, that's a chonky friend. These are our x's. But like we've talked about before, sometimes we have more than one feature, right? When we were, doing our iris data set, we had 4 or 5 features. So we can have different features. So really what this is, right? This is like all of our features here. We'll just like put it in this nice little feature package, okay? And not someone new, you say, am I uploading the streams to YouTube later? Yes, I am. And thank you for following. Okay, so this we pass, and we multiply this by some weights, okay? So, a lot of times, let's see, Tramsay 1027, thank you for following. So this is all this, X is just, it's all of our features, right? Okay, and so we're gonna multiply X. Let's use a dot to indicate multiplication here, also because it would actually be a dot product, but we'll go into that. And we have some weights. And if weights are unfamiliar, like, what the hell's a weight? Somebody who's been around for some days of the 12 days of machine learning this, how about you let them know, what are weights? What have we used weights for before? What do they signify? How have we used them? Okay, the blasting of the holiday music. Not you, no worries, Matt. It's okay, you can miss however many classes you want. And MH Scenarioman, you asked, don't worry about asking too many questions. Do we add a 1 for intercept? What do you mean by adding a 1 for intercept? I think I know where you're going, but, and Belgian, you say we use weights to get swole. Well, yes, and in a lot of ways, weights are how our models get swole. So, and let's see, yes, importance. So a lot of times when we've thought about weights in the past, purple. And Ian Alex Hart, thank you for the bits. Welcome, welcome. These weights, we can think about them as, yeah, importance. That's how we've been able to extract our weights in previous models to be able to see how important certain features are. We won't necessarily be able to do that tonight yet. But mathematically speaking, when we talk about a weight, we're just multiplying by a value that does signify in some way how important this feature is. Now we're going to do this a lot of different times, so we kind of lose the thread a little bit of one number signifying the importance, like, you know, y equals mx plus b. That was really easy to just kind of yoink our m out of there and be like, oh, phew, I know exactly how important this feature is. So things are going to get a little more tangled. Haha, see, because it's a net. But don't lose that idea that the weights are really telling us which features or which inputs are going to be important for what we're looking at. And breakpoint, oh, hold on. 17 and C is 100, 117. Breakpoint 117. Thank you for following. And Skugget, you say, careful using bias here, because we're going to introduce something else later that is a bias. But what do you mean by bias when you ask that, or when you suggest that? And your neural net tends to underweight this kind of content. Well, you know what? Train it better, my friend. Okay. So one of the problems is, though, is that a single TLU, a single threshold logic unit, it's going to struggle if we have just like a butt ton of data. So like think about our Spotify data set that we used, right? We had like 100 and something thousand cases by a whole bunch of different features. So one poor little threshold logic unit, it's gonna struggle. It's not gonna be a good situation. And so instead, we're going to, you know, ensemble, if you will, our threshold logic units all together and have them work in what we would call a network, right? We're gonna bring them all together. They're all gonna work together. And hold on. Oh, your name is not showing up. Crow, you say, why does your neural net work great on the images you use to train it on, but when you test on random images, it gets it wrong and it claims 90% accuracy? So, generic crew coming in with the answer there. Nice. So you were saying major overfitting, which is true. So it looks like if that was your situation, and assuming that what you're testing on is a different data set than your training data, that's kind of what it sounded like, I think, when you said tested on random images, it sounds like your model has overfit. So it's not actually generalizing well, it's just learning to predict specific things about your data set. Too much snow? Haha, Onad. Onad's making a stream joke, I think. Are you talking about the wolf story I like to tell with overfitting? Or like explainability? Okay, so threshold logic units. So now we're gonna put these together. So Crow, you say it claims 90%, so it should get most images correct. Well, that's the importance of the training and the testing and the validation, right? Is that it might think when we train it, that's how we get our all right, this might be, here's our measurement of accuracy. But then if you validate it on something that is completely new, that it hasn't seen before, and it does poorly, then it's overfitting. So it's I would say reducing complexity, looking at some of your hyperparameters, but largely you can, let's see, it depends on your architecture too, but if you reduce the complexity of your architecture, that can be a good place to start. Usually the way that I like to build kind of these deeper neural nets or whatever, and complicated machine learning models in general, is that I start really simple because that gives me a baseline. So I will start with a baseline that is a simpler model, and that gives me a performance that I can judge my more complicated models against, because in my mind, and this, I think this is a very good principle to follow, is that if you have a higher complexity model that cannot outperform a simpler explainable model, then you have no justification for using the complicated model. So really, for that complicated model, that less explainable model to be worthwhile, it needs to outperform, the well-tuned logistic regression, the well-tuned linear regression. And so I would recommend, whenever you're starting out, having a simple model that you use first. And there's going to be some fields like computer vision and stuff where that's going to be a little bit harder, but generally speaking, it's a good back of the hand rule to follow. Good rule of thumb, right? Yeah, okay, I said that right. I know idioms. I'm cool. All right, so let's see here. Yes, we talked about threshold logic units. And then there are lots of different ways that we can string these units together, lots of different ways that we can change their rules for how they activate. One of the simplest ones that we'll be talking about today has another really cool name, which is Perceptrons. So if you didn't think you were in the future, a name like that makes you feel like you're in the future. And so the way that we're gonna tweak things just a smidge from our TLUs, okay? And so here's the function that we're gonna pass our input into, right? So we're gonna say we've got, I always forget how to write these really well. Why am I doing that last? I have no idea. All right, this is gonna be there we go. This is going to be 1 if our weights times our inputs, our x, our features. Oh, what's this? Are greater than 0. And 0 otherwise. So this should look, again, really similar to some of the stuff that we were doing with logistic regression and thresholds. This is times. This is not a dot, well, it is a dot product, but I'm not making that distinction just yet. And Sundere Tube Worm, your name is excellent. You say perceptrons roll out. Exactly. Well, both of these are vectors. Don't drink and drive, bro. So we will be actually doing the dot product. For conceptualizing it, I want people to think of this as multiplication. And are they at war with the Decepticons? No, Transformers, because Transformers are actually a neural net architecture that we can talk about another time. Okay, so a couple of different things happening here. We have this new B term, which let's just think basic math for a second, right? If our TLU had this idea of our weight, times our input being greater than a threshold, and we subtract B from both sides and we get this, well, B really is our threshold here. And so that's a way to tweak things. So it's not just, greater than 0. We're able to add, this is called the bias, by the way. This is our bias. This is how high does our weighted sum need to be before we actually activate. So the reason, again, why we sum this, because that was a question from earlier, is that remember that we have all these x values. And then we got all these, weight values. And once we combine these, we need a single value to compare against our threshold. And that is why we sum. Yes, okay. So we've got our weights. I'll actually write all of this out for you. These are our weights. We have our input. We have our bias. And let's see, perceptron is a hard thresholding rule. What do you mean by that? And, but as let's see, who was it? Don't Drink and Drive Bro has pointed out, the math is going to be just a smidge more complicated because this isn't just W. This is W0, W1, W2, W3, et cetera, et cetera, et cetera. This is not just one feature. This is our entire feature vector. So when we multiply these together, let me get a nicer color here, purple. When we multiply these together, what we're going to get is we're going to get something that looks like this. Yeah, kind of. I think it makes sense, right? We're just multiplying each weight by its corresponding. Why did I do B's? Oh, Jess. Helps if the person telling you how it works writes the right things on the blackboard, doesn't it? All right. But I think this isn't scary. This is a very intuitive idea. We want each of the weights to multiply by each of the inputs, right? And this is something in math that we call the dot product. But just think about it like if we've got a whole bunch of components of these, we need to multiply them up element-wise, and then we're going to add them all together. Okay? And so that's also why that sum comes in, is this is a dot product. Oh no, the music is messing with you? Well, it's this is the 12 Days of Machine Learning, miss. So we are not celebrating any human, mere mortal holiday. We are celebrating a wonderful holiday of machine learning instead. And Chad B. Noob, thank you for following. What a name. All right, so let's draw, oh God, let's draw. Those are famous last words for me. Let's draw a little bit of a network here. So arctan infinity, thank you for following. All right, so what do we have? We have our inputs. And this is gonna be our X, all the way to our xn, right? And we didn't support the snoots. What? Snoots are always supported in this stream. And nope, we don't need to assume x is never negative. X could totally be negative. And so let's see. What do we need to do here? We need to multiply by our weights, right? So we're gonna, here's our input. So let's say we've got here's a little perceptron, a little, oh no! Yes, okay, the bits donation. Luftbahnhaus Hubble. Thank you for reminding me. I get distracted with the math. I get so distracted with the math. Give them some time. Okay, all right. Hubble went to the vet today. He had a whole bunch of vaccinations. He got his paw looked at, examined by the vet, so he's had a long day. He was there for some hours, actually. He's doing fine, don't worry. But we had to I think it's going to be a good idea if he has a rest really quick. Give me one sec here, friends. Just take care of something. All right. I always draw these things wrong, so I want to make sure I have like a pretty picture, because my drawing, you've experienced it, it's not great. So, all right. You missed what I said about B being bias. Bias is just a way to kind of like change our threshold a little bit, if you want to think about it like that. Okay, So we're gonna have each of our x's, right? Let's for sake of my poor drawing ability, let's say we've got 3. All right. So we're gonna, these are our inputs here, our features. This is a very easy data set, but you know what? Nobody wants to see me try to draw something more complicated. So give myself some room. All right. So then we're gonna have our first layer here. Okay, we're gonna feed it these inputs. All right, this is often called, aptly named, our input layer. Okay, so these are just our little friends, our little perceptrons, but really just think these are our function boxes. That's all they are. All right, so then let's say our next, ooh, I have a follow, hold on. Thank you for following Geico N. All right, so let's say that we have 4. Okay, and then, shoot, I want red. Let's make it red. 2. So this will be our output layer. And this little like, you know, sandwich layer of our neural net cheeseburger here, this is going to be called our hidden layer. Because really, you know, we're going to interact, we're going to feed data to the input layer, and we're going to see an output, but the hidden layer is kind of just, they're doing their own thing. And so once we have our inputs, we have our, you know, our X, 0, 1, and 3. Somebody said that, yeah. That's what happens when you talk out loud and write. So let's call this, let's say we call this A, B, C, and D, okay? So we're gonna have, oh no, I need another color, yellow. We're going to have a weight that is responsible for X0 going to little, you know, perceptron A or little neuron A. Then we're going to have a weight that's 0 to B. We're going to have a weight that's 0 to C. We're going to have a weight that's 0 to D. Not bad, right? Okay, well, here's where the fun starts. We're also going to have those same connections, but from X1. So we're going to have, you know, a weight from 1 to A all the way down to 1 to D. Same thing here. Okay. This is not a black box. No, I refuse. We're not. That is a banned word. That'd be actually really funny. Lofo, can you ban black box? It'd be really funny if that's a banned word in my stream. And let's see. So don't drink and drive, where you say that's a 4 vector. How do you work around with the 3 inputs? Well, think about it. This is just an Abram Paso. Thank you for following. I am running out of colors. Let us use orange. Gray. We'll use gray. Okay, so this is just, you know, right? This is just, let's keep it in the same order. So it works entirely because this is simply, you know, a number in this case, right? These are all our features of our feature vector, and we're going to simply be multiplying them by each of our weights. If we have 4 weights, well, then we're going to have 4 multiplications here. And let's see, why do I not like the box of no saturation? So Matt, black box is a term often used in machine learning when people don't, like when either things they have so many hidden layers that they're not really able to follow or explain well what's going on. Or honestly, they don't have the time to sit there and really test it rigorously to understand what the different layers are doing. A lot of times it is a dimensionality problem. Like you have 64 hidden layers, like that's exhausting. That's going to be really difficult. And so that's why a lot of times neural nets are referred to as black boxes, or at least the hidden layers are, because it's like, yeah, let's just pass it through a bunch of these little function boxes and hope that it works. And no, so Crow, you asked, does the machine get better if we put more and more layers? Absolutely not. It's kind of like when we were picking K, right? Where for our K nearest neighbors, where there's going to be a good amount of layers to use, and if we go too far, we get too high of complexity, we might run into overfitting, we might run into performance problems. Okay, music, there we go. And if we put too few, we'll run into performance problems because it's not able to generalize effectively. And okay, so hopefully that makes sense for how we can have four neurons in our hidden layer, but we can have 3 in our input layer. And no, I can't have the lights right now because I have the green screen. I'm sorry, Sweeku. So I have to pause the fun changing of the lights while I have the green screen up, because otherwise it really messes with it. Okay, and so then oh yeah, look at this excellent drawing. Okay. But really, if this is starting already to feel overwhelming to you, just think about this like function boxes, like we've been talking about. I'm going to pass it a value, it's going to perform a mathematical operation, and it's going to, spit out a value that then gets passed on to another function box. So in this sense, we are chaining our function boxes together to create a network. And what's really important here is that if remember how we were talking about that threshold, right? So the threshold for activation. Well, what does that even mean? Why does that matter for something like this? Ask R. Vidar. Thank you for following. So the activations in one layer are going to strongly influence the activations in another layer. So let's say we're gonna go real basic here, okay? This is not how neural nets necessarily work, so before anyone gets cranky in chat, but I want to talk really simple for a sec. So let's say we've got the number 4, the number 7, and the number 11, okay? These are inputs, and let's say we have the most basic kind of situation here where, okay, here's our input layer. And instead of worrying about weights and things like that, we're going to really simplify it, okay? Common Magpie, thank you for following. Our function boxes in this case are going to be addition, okay? And so it's not even an activation really, but let's say that if our input plus a certain value, we'll call our weight in this case, is greater than 20, we activate, okay? Hunter Solo, thank you for following. So maybe this one does +2. Well, actually, hold on. So we're gonna make less, otherwise we're gonna get way too many drawings. So can I move this? Will it let me? Yes. Okay. All right. You know what? I will just rewrite it. Okay. So let's say that this adds 2. That's a 7, not an adding. This adds 3. And let's say this subtracts 3. Okay. So let's follow this one little input. Then what happens? So this little input gets passed here. 4 plus 2 becomes 6. 4 plus 3 becomes 7. 4 minus 3 is 1. Okay, so now these values. Now what's the rule here? Well, let's say that the rule here is we're going to add 10. We'll add 4. We'll add 3. So then, I need one of these to make 20. Hold on. Let's say this is adding 20 for the sake of argument. Okay, so this adds 20, and we end up getting 26. Oh, so this is activated. This is really strong. We've got, let's say that this is adding 7, so we get 13. Maybe this one over here is going to subtract 1. We get 3. Anyway, you see the point. If this adds 20, it's going to affect future layers and how they activate and their rules. We are simplifying imaginarium. We're going to just use adding for a second so that we can kind of understand the flow here. So when we feed our data forward through the network, and in this case, we're just adding. And yeah, right now, Suiku, we're assuming every single layer has the same activation, which is this rule. We're not overcomplicating it. Super, super, super basic. Oh, is the background music too loud? I will fix that for you. There we go. Hopefully that is better. If this, for example, had a much, much higher value, maybe this was plus 50, who knows, right? Well, that's going to affect, even if this ends up being minus 10, that's going to affect whether or not the next like this neuron activates. And so the activations of the previous layer, while they don't determine what happens in the next layer, they do influence it. And this is going to be really important for later, right? It is a network. These things are connected. What happens in a previous layer does affect what happens in a later layer. So, if you are already kind of like, oh God, these circles are stressing me out, I don't understand what's going on. Anon, 0p, thank you for following. The way that you can think about layers conceptually. All right, layers. The way that you can think about layers conceptually is just think about them like the process that human beings do of breaking a problem down into smaller kind of like sub-problems. So let's say that I want to train a neural net to tell me if this image is of a dog or a cat. So, well, with my drawing, who knows, right? All right, so we have an image of an animal. We're like, oh, we don't know. Is this a dog or a cat? And Kinaguri, thank you for following. Well, let's draw a conceptual neural net here. So when you are trying to figure out if an animal is a dog or a cat, what kinds of things do you look for? Seriously, I'm asking all of you, what do you look for if you're trying to figure out if it's a cat or a dog? And Kevin KC56, thank you for following. All right, so nose. Let's look at the nose. This is gonna be our nose layer. All right. So we're gonna feed information about the nose here. So then we're gonna get output information about the nose. Maybe what next do we want to look at? Well, yes, generic crew, dogs and cats both have 4 legs. Size. Okay, so maybe our next layer is our size layer. Okay. So I don't know why I switched back to green. So now if we have, I guess, let's say a small nose, a medium nose, and a long nose. Okay? Johnnyman9, thank you for following. All right, well, this is like a medium nose, okay? So maybe, after we train and after our neural net's really good at this point, all right? No, I want sparkly. Well, this weight here is going to be really, really strong because we know, all right, this is our medium nose, okay? And then maybe size, again, small, medium, large. Let's say we feed the values here. This is not fully how they work, but I think conceptually this can help think about things. Okay, so if we feed our medium nose, all right, this is gonna be a large dog, right? So, oh yeah, all right, it's a large dog. And so then we have an output here of cat or dog. And we feed now all of the facts that we've extracted here. We've extracted nose, we've extracted size, we feed it, and maybe this says, okay, well, I guess there's some wonky looking cats out there, so it's going to say it thinks this has got like a 0.1% chance it's a cat, and it's going to give me a 0.9% chance that it's a dog. Okay? And so if conceptually, if all the stuff we were doing earlier with the weights and everything wasn't making sense, don't panic. Think of it more like this, that while sometimes we don't know how a computer might break down a problem like figuring out if it's a dog or a cat into these layers, we might not know explicitly how it wants to break it up. It's kind of conceptually what it's doing. And so for us as human beings, maybe we're only looking at the nose and the size of the animal when we're figuring out if it's a dog. And so this might be how our activations, might look. There we go. I'll finish that. All right. Rick Marinovich, thank you for following. Okay. So let's see here. In this particular case, we've talked about kind of our function box, our neuron, right? We've talked about our inputs. We've talked about our weights, our bias. Well, now we need something called an activation function. This is going to determine if that neuron activates. Okay. Doop, doop, doop. And who remembers our function from logistic regression? Even if you just remember what it's called, that's totally fine. And Aaron Petrio and Zoggy, thank you for following. So who might remember log 2 plus no yes, okay, MH scenarium, yes, sigmoid, everyone, sigmoid, okay, precisely. It's a very easy way to get a binary output from a numerical input, right? So we're going to return, oh no. Okay. We're going to return to our good old friend, the sigmoid function, which is the S function. Again, I'll put the math up here, but don't panic if the math is already kind of like, oh God. This is just the point that you need to remember here is that this is the function where we give it an input and it's going to output for us. It's going to squeeze our value into, this is going to be 0, this will be 1. Okay, so it's going to take whatever it is that we feed it and it's going to compress it. It's going to squish it between 0 and 1. And I Villegas Belmar, thank you for following. Can you get extra credit for log 2? It's okay. I appreciate the response, shall I say? And so remember, yeah. So we used this in our binary logistic regression, and you can have a lot of different kinds of functions. So there's as many activation functions. I mean, there are the tried and trusted ones, but there are a lot of different ones that you can use. So I'm sticking with the sigmoid function because we've done it before in these streams. And also, for what I'm going to use later, it's going to make sense if I introduce this. And Purge Time, thank you for following. Loaf Phone with the gift subs. What's your new number that you want to get to? Because it was 69 for a while. 169, oh God. All right, well, you'll be here a while. But I'm so glad now Metzger9, Virtual Assistant, East on Coast 7, Goofy Lagrangian, and ViewStyle 150, you have subs. So you've got pictures of my dogs. You've got the burger emote, which is really fun. So now hopefully you will you'll stick around for the rest of Machine Learning Myths, I hope. And thank you also, Loafbone, of course, for the support, I guess. for the subs. Thank you for increasing our streams community. It's always good. I like to have more people in stream, more people learning and filling out our community. I love to learn from you all, so it's awesome to have a bigger community. So thank you. Okay, so Oh, is that an L? No, Samuria. Thank you for following. Dodge the subgift. Oh, what's wrong with subgifts? And like I said, generic crew, Raylu is perfectly fine. There are all different kinds of activation functions. For the sake of something I'm doing a little bit later, we're going to use sigmoid. Also because, like I said, I've introduced it in previous machine learning streams, so it's going to be a little more familiar for folks. So the math is going to be, it's going to look like, okay, it looks like some math, but it's all right because we remember our S function. And PR Datter, thank you for following. Low phone your sass. Okay, well, I'll do you didn't escape, I guess. now you're stuck. You thought you escaped the gift subs, but you did not. And so okay. So now that we've been introduced into our activation function, I am going to do just a little bit of terminology recap before we move on into our first segment of math, okay? So terminology. We've got our neurons, right? Which you can think of like our function boxes. Random Cake 2, thank you for following. And Beast GG9, I don't think I have a sub count. I had a stream goal to hit 100 by New Year's Eve, which we met. But actually I can try to do that for a future stream, but I do not have I don't have a sub count. Usually the sub count has been quite low, so I just haven't really bothered with tracking it. And add them all together. Thank you for following. Okay. So we know we organize our neurons into layers, and we understand conceptually at least our layers as being the computer's way of breaking down a really complicated problem into components or into sub-problems. And Ian R. Livingstone, thank you for following. And Onad, you say you'd like to donate $301 in spirit. Your spirit donation is greatly appreciated. Exactly, Low Phone. That was a very surprising donation. That person was very sweet. And it was wonderful because after stream, we were able to raid a really tiny stream, and I was able to gift a bunch of subs to that tiny stream and pay it forward. So, MH Scenarium, you ask, and Prutz1311, thank you for following. You ask, would you explain the difference between neurons and layers? Yep. So a neuron is a single unit. So remember, like when we were talking about our threshold logic unit. While we aren't using TLUs anymore, these are our function boxes. When we chain a bunch of them together, we get a layer. So this, a bunch of neurons together, is a layer. So a bunch of our function boxes all chained together, working together, that is our layer. And hi, Prutz1311. Thank you so much for following and welcome. Okay, so what else do I have to make sure that you understand? Okay, weights. And virtual assistant, thank you for the bits. I like the countdown, all the cute little hearts. Weights, which is something that we've learned in previous machine learning streams. So weights are a comfortable idea for us already. We also talked about our bias, which is not used in the sense you'll hear people talking about algorithmic bias. They're talking about something else. So this is bias as in that additional term when we have, our sum of our weights and our inputs. Well, that's going to be plus a B, and that B is our bias. So it's going to be that offset for the threshold. It's our way of affecting the threshold. Simply Alex 6, thank you for following. And okay, so what else do I need to make sure? Yes. Okay, so if I do, oh God, the drawing for this is the worst. All right, so we're gonna keep it real simple. I'm gonna draw a really, really basic one because, man, I'm not. Oh yeah, okay, this isn't the worst. And this whole thing, right, is our network. Each of these is our layer. We have an input layer. We have a hidden layer. and we have an output layer. Is my head in the way? I'll just duck. All right. And thorough away. Thank you for following. And Simply Alex6, if I didn't get you, thank you so much for following as well. So Skugget, you ask, is this like the B in linear regression algorithms? I don't mind if you think about it that way. So while the math is going to be a little bit different, that idea of that kind of offset, so right, that B in a lot of ways is how offset that line is, right? That is kind of a similar idea. So it's okay if conceptually you want to think about it like that. And Ian R. Livingstone, thank you for subscribing. Oh my goodness, welcome, and thank you for supporting the channel. I appreciate it. And B88E, thank you for following. Okay, no, I'm not drawing a pentagram. Hidden layers. All right, so as we move along these connections, right? This is where I am seriously hurting for colors here. Curse only being able to see in the optical spectrum. Our weights are applied as we move between, each of these is going to have a different weight, right? So our connections here, sometimes you'll hear them called edges. Those are each going to have weights. They are going to determine for us how important those values are as we pass them through our network. So just like in our linear regression, just like in our logistic regression, our simplest of models, training, I am going to run into my own face. All right, hold on. Do I have room down here? I'm trying to, see, I'm doing better, I think, about making it not one giant line of notes. Our training, what is training in machine learning? What is training in machine learning? What are we hoping to do here? I know, Onad, it's my secret superpower, isn't it? Ravenous, thank you for following. Not run models. What actually is, when we talk about these components, the neurons, the layers, the network, the weights, the bias, when we've talked about training before, when we've been training our models, what is that actually doing? Yes, Dieticus coming in with the answer. And oh, bye, Skugget. I'm glad that you were able to stop by. You got a study that is very important. Okay, exactly. Lots of people coming in here to answer correctly that training is about calibrating or figuring out, I will say determining the weights. And in this case, let's not forget about our biases. So training, right? Now think about this. You've got this network. You've got all these little function boxes hooked up together. And how important the outcome of each function box is determined by these weights. And so tuning it is a lot like tuning an instrument to get a chord, right? We have to make sure that, even though it's part of a bigger whole, each of these neurons has weights applied to it as it moves forward in the network that result in it getting the correct answer. And so how does that work? Well, we're gonna have to do some math. This is where we're gonna get into some mathiness, which yay. Oh no, why is this working? Mouse, please. I have too many things in front of me. There we go, little mouse. All right. So let me just do a quick check here on how my, okay. So I'm gonna move down here now. I'm trying for you guys. I'm trying to make it a much, much nicer series of notes than previously. Okay. So, and can I drug the neural net by lowering the thresholds? If we were to, you want to tune the thresholds, right? You want to tune the biases, but I'm not sure what you mean by drug it. All right, so how do we learn? Learning, how do neural nets learn? Neural net. Oh my God, this is so frustrating. I need like a desk that is 5 times as large as this one. And I'm a small human, but I need a lot of room. All right. I am going to go grab another beverage. And while I do, I have a question for all of you to think about. So, how did previous models we've done, or if you already know some stuff about machine learning, that's great. How did previous models learn? And learning, we just talked about how do we figure out our weights? Okay, I will be right back. Give me like 30 seconds, but think about this because I want to connect this to our previous models, okay? So take a second, recap, make sure that, so far you understand what's going on. And when I come back in literally like 30 seconds, I will answer any questions that you have right now, but also hopefully we'll be able to remember, hopefully you haven't forgotten everything. You'll remember how our previous models were able to figure out weights. And Yo Yabba Dabba and Wavis RT, thank you for following. I'll be right back. Okay, all right, so, let's see here. I'm catching up on chat. So, views to say rules-based learning. Well, we're trying to avoid that, right? That's the whole point of our machine learning. MH Zinnerman, you say lowest root mean squared error and also lowest sum square of error, or squared sum of errors. Some of the squared errors. Yes, you are very, very close. But what are those called? What you say, we do it via error. How do we learn from error in machine learning? And what do we call that? Quiz time. So this isn't our reinforcement learning. And it isn't necessarily optimization. So I seem to be probably phrasing things terribly. So forgive me and let me try to rephrase this. So in previous models, how we determined our weights was through error, an error function of some kind, right? And what was our goal with the error function? Our goal was to minimize it, right? And through minimizing, however we were measuring error, we were able to we were able to update our weights, figure out what weights we needed to be able to reduce and minimize our error function. And ViewStyle150 coming in with the word that I really wanted to get to, which is that we also call this our cost function. And that's what we're going to use today. And so just like with logistic regression, just like with our decision trees, we are going to use a cost function or a loss function or an error function. We got so many words for it. And we're going to attempt to minimize it. But previously, it's almost been like we've had one neuron that we've been dealing with. We've had one function that we're passing things through. Now we have a whole bunch of them. So just like the lay of the land's gotten a little bit more complicated, it's also our cost function is also going to get more complicated. Okay, so what we're going to use today is something that we've used previously, which is sum of the squared difference, okay? Which is I will abbreviate it frequently in code and stuff like this. Sum of squared difference, right? And all that is it's going to be a sum and squared difference. So it's going to be the answer, the right answer, minus our answer squared and the sum of those. That's a good point, Onad. So you say, why not SSD? Some of the squared errors, I guess, is the way that I thought about it in my head when I was writing it. You could use some of the squared differences. Yeah, whatever. I think previously I also have used SSDS in one of our streams, just because it reminded me a little bit of the Sloan Digital Sky Survey, which is SDSS. So whatever abbreviation you choose is totally fine. But we need to think about this a little bit more mathematically, okay? Because, previously, what did we do? We had, a cost function, a loss function, whatever, that would take in our right answers, the truth, our labels, right? These are our labels, and our answer. And, we would kind of just, like, all right, we'll just minimize this function, and that's what tweaks our weights, right? And ICOG, this is a common cost function used. And so when we square it, think about it actually. Think about the math for a second. Seg Pamafote, thank you for following. What happens when we square a really, really small number? When we square a really small number, it gets, it doesn't change as much, right? But when we square a big number, that number is going to get really, really, really big, right? So I think you can answer your own question here. How would these two be different? Well, let's take one case where we get the right answer. There wouldn't be any difference between them when we get the right answer. But when we're really, really wrong, the squared error is going to penalize us so much harder versus a simple sum of the difference. And so a lot of times we're going to use sum of the squared differences because when we're really wrong, it's a punch to the gut. It's like, no, we are going to square how off you were. And that makes it so that, we are minimizing those large errors more quickly or more effectively, if that makes sense. Hopefully that answered your question. Developing that kind of intuition of I have a question about this, but wait. Let's look at the math. Think about the case where we're wrong. Think about the case where we're right or the case where we're wrong by a lot. How are they different? And then you can kind of answer your own question almost. And then Grateful Tomato, you say, tomato. You say, do the usual networks have feedback connections from the output to the input? And would the weights adjust work for it as well? Hold, please. You are skipping ahead, my friend. We are not there yet. The connections that you're talking about for the output to the input, we will get there. And that's something really, really cool. But first, we need to understand how we are going to calculate error and before we even talk about how we're going to adjust weights, right? So if we're going to break down our learning into some steps, our steps might be we need to figure out We need to calculate our error. We got to figure out how to update our weights based on that error, right? And then like test again or go through again. Okay? So we are at here. You are talking about step 2. So you're just thinking ahead, which is good. I'm glad your intuition is going there. And Ermi6, thank you for following. Okay. So, how do we learn? How do neural nets minimize their cost functions? All right, Vendo Fiesta 0304, thank you for following. I'm going to introduce a jargon term, technical term, that you've probably heard if you've been trying to Google about machine learning. But don't worry, we're going to go into it literally word by word. So it is called gradient descent. Okay. So I'm gonna give you a really, really basic example. Let's say we have a really, really simple cost function, okay? Let's say our cost function looks like this, okay? So this is our cost function. How much we suck. Here's a measurement. Well, we want to minimize it, right? Well, that means we really want to be here. That's the minimum, okay? How do we figure out the minimum of a function? How do we figure out where, if we were to plot all possible inputs, here's the pattern, right? Here's our y, here's our x, all possible inputs to, actually I'm not going to use y here, I'm going to use cost. Yes, oh good, okay, so people are answering the derivative equals 0. And so do not panic if you have not taken calculus and you're like, oh my God, what the hell is a derivative? Deep breath, okay? All the derivative is it's like a complementary function to this one, that for any function, any possible pattern that you can think of a function, we're going to have a derivative which tells us what the value of the slope is at any point. So this gives us slope at each point. And apparently I've chosen white for the derivative. So let's draw the derivative. Let's draw it. What is the slope? And I should say, we are using Western writing convention. We move from left to right with our functions. So if we start all the way up here, how steep is this part? What is our slope? How steep is this? Is it positive or negative? This is quite steep and it's quite negative. So let's just say, I'm gonna extend our little graph here. Let's say we're down here somewhere. Okay? I'm actually gonna do that. Okay, now what about here? Are we still negative? Are we positive? How has it changed as we're moving through this function? And Belganul, you say the derivative is 0 at the maximum as well. Yes, hold please. Hold. We will get to that. Negative but less steep. Okay, so we're still negative but a lesser negative value. Okay, so maybe here. Okay, what about here? Less negative. All right, and here it's at 0, right? I'm actually gonna change this color to red because this is where we want to be. It's where it's 0. Okay, now what happens when we start moving up the other side of the curve? Well, it's no longer 0. It's positive. And as we move up this, we're getting steeper, so our value is getting higher. And we end up with something, this is again, bad drawings, bear with me, something that roughly speaking, oh Jesus, all right. I can do it. I'm gonna change that so it fits. No one is about to see this at all. You see nothing. If only it worked like that, am I right? Oh, this doesn't fit my line. I'll move the data point. Don't actually do that in real life. All right. And so this is the derivative of the cost function. And it's handy. We now have this cool thing called the derivative where we can figure out what the slope is of our function at any point. Awesome. And Vienta0304, thank you for subscribing. Thank you so much for supporting the stream. It is greatly appreciated. And hello, Yanis. Let's see, negative, but let's see. Yes. Okay, so if those of you who haven't taken calculus yet, this graph right here that I drew kind of looks like, if you remember from, oh God, I'm having to change colors, should kind of look like a little bit, my drawing's terrible, but you know, it's fine. Kind of looks like this, right? And the derivative is linear, so it's gonna be of the form something to x. Those of you who know your derivatives know it's gonna be 2x. The 2 hops down. Should the red points be vertically aligned? Yes, they should. Yes, they should. I tried to keep them separate so I wouldn't be overlapping these and inadvertently made the world's worst math graph ever. So this is really what we were looking at. So thank you for that. They should be, yes, but it got really cluttered, and so it started out as a conceptual graph and I tried to make it mathematic, but so a lot of times you'll see this little apostrophe used for the derivative, but I'm going to show you something slightly different. The other way that you might see the derivative done is dy dx, where y is our cost function, right? And this d is just delta. It's like a tiny delta. So this is asking, how does y change? I will move, hold on. How does y change when x changes? And this is important, right? Because the two things, even if you're like, oh God, I don't want to do the math, no thank you. The two things I want you to take away from the derivative are, gives us slope, mathematically speaking, and conceptually speaking, it's asking us, how does something change with respect to something else? How does one variable change with respect to another? Or, you know what, I'm going to say it even more plainly. How does one variable change when another one does? So when another changes. So how does y change when x changes? And Deirdre, you say you don't understand the difference between partial and normal derivatives. Don't worry. Hold on. We will actually have to do some partial derivatives. I'll introduce them conceptually though. And MH Zanaraman, you say, before we leave the calculus, we're not leaving the calculus yet. We have barely scratched the surface. So hold on to your convexity question. So, all right. Those of you who don't know calculus, those of you who don't do the math, do you at least conceptually, even if you're like, you don't know how to get it, that's fine. You don't need to know how to do the derivative right now. Do you at least understand kind of theoretically what the derivative is trying to do here? Because I want to make sure, we're going to use derivatives throughout all of this, so I want to make sure that you feel comfortable with the idea. This is, a companion function to any function we have that gives us our slope, and it allows us to have a measurement for how a variable changes with a relationship to another variable. So if we only have two variables, it's very simple. We can ask ourselves, how does y change when I change x? How does that feel? Do you feel good? Are derivatives your new best friend? I hope so. Grab your convex butts. No. Well, nobody's crying, at least from what I can tell in chat, so I will move on. But if you do need to cry, seriously, stop me. So this was an example with two variables, an output and an input. Real basic. But we know better than that. We are seasoned machine learning, developers at this point. We have built machine learning models to handle inputs, X's, that have, 20, 30 features. Oh God. What now? Well, have no fear. So, okay. And yes, Wolfram Alpha can do it for you. I would say if you really are interested in studying machine learning more in depth, a good solid refresh of calculus is awesome. But that's also why we're going to be having Math Mondays. So don't flee just yet. Okay, so if it's really complicated, if we've got our 50 different features, we can't brute force it. We can't sit here like, I know it was deceptively easy that I just so quickly, those of you who know calculus are laughing at me, but it seems, if you've never done it before, it seems so simple to just go from y equals x squared to, y prime, the derivative of y, being 2x. Easy peasy, right? Well, if we have 50 different letters here that we all have to figure, how the hell do we do a derivative of that? Well, you know what? It's going to be brutal to try to brute force this, especially if we have all of these different weights and all of these different biases, and we've got all of our different neurons and all of our different features. Okay, like things are getting horribly complicated. So instead, what we're going to do is we're going to use some more awesomeness that is in math. Okay. And to understand what we're going to do conceptually, I want you to imagine that you are playing some kind of horrible hiking game. Okay? And the goal of the hike is to find the valley. All right? But you're blindfolded. How the hell would you be able to tell if you're headed in the right direction if you're blindfolded and your goal is to get to the valley? You're playing Death Stranding. There you go. Yeah, low phone, whatever. But you're blindfolded. Playing Death Stranding. You're in Death Stranding. Okay, you're torturing it. Leave it. You're a hiker. You're blindfolded. You got to get to a valley or even the top of the highest mountain. How do you tell whether or not you're headed in the right direction? Not that you found the peak. How do you tell that you're at least kind of going in the right direction? Slope. Why slope? And you can't look up, low phone, because you're blindfolded. Right. Uphill or downhill, which is just slope. So if I'm a hiker and I'm heading consistently downhill, I might suppose that I'm headed in the right direction. And so what does that process look like? So if we were to imagine ourselves as a blind hiker, we might take a step. Okay? We might, stick our foot out and kind of feel around and be like, all right, which direction is downhill? Not just downhill, but is steepest downhill. And we take a step in that direction. And repeat. Well, this conceptually is all we're going to be doing with the math today. So if derivatives are our way of finding slope, we can imagine if we are in this very simple two-dimensional land, like I'm a little hiker trying to find the valley. Bujusima, thank you for following. We can imagine taking a step and going, am I going downhill? All right, take another step in that direction. Oh, if I'm going up this way, if I'm moving this way, hey, that's not the way I want to go. That's uphill. I want to move downhill. When the space of our function changes a little bit, I have a picture because I'm not going to draw this. I'm not going to subject you all to the horribleness of my drawing. So let's I have to be so careful now that I'm putting these things on YouTube, like what images I show and like what music I use. It's been stressing me out a little bit. Okay, so let's take this picture. All right, These are our hills. That's all this is, okay? No pumpkin spice, Pascal. Don't worry. We are gentle math here. Gentle derivatives, happy derivatives. Okay, so as we're stepping, we can imagine ourselves being a little hiker, moving along this terrain, trying to find the steepest lowest point, right? Well, there are a couple of things that might affect it. First of all, like you've said, what happens if we get stuck in a local valley? Well, some of that is determined by what we're going to call step size. And I want you to imagine for a second that instead of just being, a mere mortal hiker, you're a freaking 25-foot troll hiker. If you take a giant step, well, you might find the area of descent faster, but you also might step over repeatedly. Like if the width of my stride was the width from this peak to this peak, I might find myself continually stepping back between the two of them, not able to find the bottom. So in this case, step size is something that we'll be able to control, and that's an important part of figuring out the lowest point. If our step size is too tiny, if instead we're an ant trying to crawl around here, it is going to take us freaking forever, and we're going to be more likely to find a local valley and not the deepest valley. And John the Marksman, thank you for following. And in this case, the terrain doesn't represent our weights. This is our error. This cloth, this beautiful looking terrain here is our error. It's how much we are sucking at doing what we're supposed to do. So yes, we want to find the lowest valley. We want to find out where our error function is the lowest because we don't want to screw up anymore. And Goofball Guinness, thank you for following. And Pumpkin Spice Pascal, you say, you loved math until you hit Calc 2. No, you say that had a lot of tears. You work with a pharmacist that went into Calc 3 because she was going into mechanical engineering. Well, mechanical engineering sounds cool. Do not fear calculus. I hope that, you stick around and stream and you'll be here for Math Mondays. I'm actually going to start all the way back with algebra. So if, algebra is easy to you, you will get a solid refresh. You'll be able to help out in chat. But I'm going to move as far as I go until people start to not watch anymore. So we can go, differential equations. We can do however much you all want to do. But calculus is where, at least for me, I thought math got really beautiful. So I hope that you will stop by for the Math Monday streams and I can show you that calculus can be very beautiful, because I think it can be. Okay. So we are going to use, I'm using my stylus, not my, all right, so I wanted a 3D example and I didn't want to draw it. So that's why we got the fun rainbow terrain there. So how do we figure this out? So what we're going to do is we're going to use a happy little thing in math called the gradient. I'm not going to teach you how to do the gradient because that's for a Math Monday stream. But what you can think of with the gradient, if you see it, that's ugly. It's kind of like an upside down triangle is what you'll see with the gradient. And what the gradient is going to do is it's going to give us the direction of the most positive change and the magnitude of the change. So, and how steep. So think about it, it's going to tell us the direction of the hill and how steep that hill is. And so what we're going to need to do for this, right? Well, we're taking the gradient of a cost function. The cost function is a bad thing. We don't want to be making a positive. We don't want a steep increase in our error, right? So we're going to be using the negative gradient. We're going to be using a negative gradient to descend to the lowest valley in our error function. And that is where we get gradient descent, okay? And don't worry so much about the math just yet, because if you haven't done the math yet, I'm not going to sit here and teach you how to do the gradients, but understand at least that this is going to be a cool math tool that we can use that gives us these two outcomes. So just like the slope gives us direction of change and how steep, right? Because like if I have a slope of -10 versus a slope of +4, right? It tells me direction, negative versus positive, and it tells me how steep, 10 versus 4. So this is just, this is when slope has leveled up. It has evolved like a Pokemon into something way cooler. Slope has evolved into gradient, and we're going to be using it to find the lowest points of our cost function. Okay, so now we got this. All right, so we're trying to minimize our cost function, right? So gradient descent tells us which direction and how steep is it. To take a step in that direction, what does this require? Like as we are thinking about this from a machine learning perspective, from our neural net, if we just feed our input back into our network, we're going to stand still. We're not going to change. So we're going to need to change things in order to take a step in that direction. We're going to need to change our weights and our biases. And this is going to be done through a method called backpropagation. So if gradient descent tells us which direction we need to head in and how steep it is, backpropagation is what's going to allow us to take steps in that direction. Oh, thank you, Dennis Bot. You say such a beautiful comparison. Well, thank you. Hopefully that makes some good sense. Let me see, where am I in my notes? Okay, this will be the happy backpropagation section. Little backprop friends. How does gradient descent feel? Again, no panic if you're like, I don't know what a gradient is mathematically. Like, I don't know what the math is. Right now, all I want you to do is to be able to understand conceptually what it's doing. Backpropagation. All right. And Ura Harakis, thank you for following. And also Goofball Guinness. I think I missed your follow. I'm sorry. Thank you for following. Let's take a deep breath. Like 2 hours in, you are powering through this neural net stuff with me. Hopefully you understand what neurons are, our function boxes. You understand the connections between these neurons, right, through weights. You understand what an activation function is doing. You understand how we learn with neural nets through gradient descent, and through, you at least know the word now, backpropagation. So before we move into backpropagation, which is where a lot of people get lost, a lot of people get scared. Don't be scared. I got you. This is like, if we're going back to the hiking thing, we're all like attached to one of those like hiking cords, right? I've got you. You're not going to fall. But I want to make sure before we move on that later, when we're building this in code and we're building our gradient descent, or we're building, the structure of our layers, that you're not like, oh God, I don't know what's going on. No being scared, loaf bone. I've literally explained neural nets to you plenty of times. You are not allowed to be scared. You're the mod. No fear, no scared mods. Okay. While you all are thinking of your questions, I'm gonna draw us another little picture. Actually, you know what? I'm so tired of all the circles. I'm gonna draw this really simply. Input, output. Okay. Math Pack, thank you for following. When is the homework due? No, there's no homework. This is a fun stream. Like, there's no homework. And yes, non-dairy neutrino. So that is what I mentioned over here, is that, oh Lord, where'd it go? I mentioned that we are going to need the negative gradient, because the gradient gives us the direction of the most positive change. And so you're absolutely right. We're going to need the negative gradient for minimizing our error, minimizing our cost function. Okay, so moving on to backpropagation, which I can't tell you how many times people have been like, oh, neural nets are cool, but backpropagation. Because the math, if you Google it, this is where the math can be scary, but it's not going to be scary today. So what have we learned so far? Well, our awesome gradient descent friend has told us what changes we need to make once we get the output, though. So hold on, let me answer a question from chat. Oh, now do you say this is confusing? A positive gradient is opposite. No. So think about it like this. The thing that we're measuring is error. A really positive error isn't a good thing. So I can absolutely do the positive gradient of my error function. But if I do that, it's going to tell me how to maximize my error. That's not what I want. I want to minimize my error. And so minimizing error, I want to say, hey, which way is making this smaller? Negative gradient. And that's why we want to descend in our gradient descent. And hi, Mediocre Gamer. Welcome. Okay, so we have our input. We understand how we pass values through our network. We multiply by weights. We feed that to our activation function. And when we get answers out the other end, we're going to feed all of that into gradient descent and go, what needs to change? So if you want to think about this again more conceptually, gradient descent tells us what changes need to happen. But not how. Backpropagation, backprop as we'll gently call it, backprop tells us how. Because think about it, right? If we go back to the very beginning of stream when we were talking about the interconnectedness between all of these different neurons, right? When we have one layer, I told you this before, that the activations of one layer they influence the activations of the next layer. So if we just know, hey, like you're off by 3 at this output, cool. How do I know how to tweak the weights 15 layers back if I just know at the output, oh, like I need this to be different. And so backpropagation is going to help us figure out how we kind of propagate, how we move backwards through our network and fix all of the weights, update our weights and biases so that our neural network is more accurate. Okay, so what does this look like? First of all, I want to give you, let's say that I'm gonna highlight things with red and green, okay? So obviously holidays, right? Green is gonna be a very high weight or large weight. Red could be small weight. Small weight. Oh, bye, Diraj. Thank you so much for stopping by. Okay. All right. So, if we have a very large weight, and let's say that, if you look at this particular neuron right here, let's consider this neuron. This particular neuron is getting 3 inputs, right? 2 smallly weighted inputs, lowerly, fewly, whatever, tiny weights, tiny weighted inputs from these neurons, and one hefty weighted one from the middle neuron. So if we want to change the value of this neuron that it outputs, what do? RK selection theory. Thank you for following. And Bearlicious, you say, sorry if this is a stupid question, no stupid questions, but does a sort of backpropagation apply to linear regression? So not necessarily, because linear regression, I would rather you think of linear regression, at least the kinds of linear regression we've done, as almost like a single neuron. It's a single function box. We don't really need something as hefty as backpropagation. There are cases where we can apply backpropagation to other models, but at least in this case, the reason why we need backpropagation is because we have all these complicated relationships between all of these different functions. That would not be the term for adjusting the weights. So if you're talking about linear regression, you would just talk about training. And do the weights coefficients have a name to describe them, or do we just call them neurons of different layers? Weights coefficients. The weights themselves are coefficients. So when we have kind of like what each the mathematical operations that each neuron applies to the input, right? We have the input times a weight plus a bias. And all of that is going to be fed into our sigmoid function. Pardon me. And MH Zinnerman, you ask, what is the difference between backpropagation and gradient descent? Right here, friend. Gradient descent tells us what changes need to happen. Backpropagation tells us how. So gradient descent is going to tell us which direction we need to go in to minimize our cost function. Backpropagation is going to make the changes needed. So this is the what, backprop is the how. But back to this example. If we have this one neuron that is receiving 3 inputs, and 2 of those inputs have really tiny weights, and one has a really big weight, which would be easier? Trying to massively increase the weights of these? Well, they're not contributing very much to the outcome. Or simply tuning the neuron that is most heavily, the connection that is most heavily weighted. Exactly, Stannis Forking. You say change the large weight, precisely. So in that sense, we're able to kind of get away with fewer changes by being really efficient by looking at our weights. And so to break this down again, right, we have our output, we feed all of that. Gradient descent is telling us stuff's got to change. We've got to make some changes to tune this. And so because all of these layers are connected, we have to move backwards through the network and propagate the changes. We don't want to just change one connection here at the very end, because what if the problem is further back, right? Since everything's connected, we need to propagation, those changes backwards through the network, hence the name. And so mixed radix, you ask, how do you avoid getting stuck in a local minimum point? And be sure you can find the minimum across the entire graph. So this is actually a challenge with machine learning, with neural nets. I have 2 answers for you. The first one is that this is why step size is really important. And it's often why your step size, we'll learn a different name for that later, but going back to that idea of the hiker and the size of the steps you're taking, that's why you might want to start slightly larger, but decrease over time or make it proportional to the slope that you're on. Because then as you get closer and closer and as things start to flatten out, you'll take smaller steps, but at the very beginning, you're taking larger steps to find the steepest drop. But honestly, there's a really, really, really cool aspect to classification neural nets, at least, where, and actually, now that I think about it, probably regression, where if you have a really well-balanced data set, you will have equal local minimum. And this is really cool. So the way you can think about it is that while our one function kind of looks like this, right? So there's only one, and maybe if I'm not super balanced, maybe this will be my error function, my loss function, my cost function. And so yeah, I might get stuck in this local minimum versus this deeper minimum, right? But if I have a really well-balanced data set, what actually happens is that they're equal. And so it doesn't matter if you get stuck in a local minimum because the value of the minima are roughly equivalent. So that's also a really cool aspect to neural nets and to like the math of the gradient descent. But the challenge there, of course, is that it puts the burden back on the data. And as we've talked about plenty of times in stream, right? I don't have a no swearing thing on, so shit in and shit out, right? So it doesn't matter if you have the most elegant neural net architecture in the world. If you feed it crap, it's not going to learn from it. And so the better our data could be, the more we do spend time processing our data, cleaning it, balancing it, doing our best to give our neural nets or our, models in general, the best foundation on which to learn, the better our outcomes will be. Okay. So, sigma, input y, input y's, yes, backpropagation, we're moving backward through the network. What else do I need to do? It's important also to say, though, that this step, currently with our understanding, and MH Zanarman, an exhaustive search, like I talked about at the beginning, neural nets, this is why neural nets, generally speaking, are reserved for, well, you need a lot of data for neural nets, more so than sometimes for other models. And often they're used and reserved for very high dimensional problems. And so it kind of precludes being able to do a brute force search. The whole point of using a neural net is that you probably can't do a brute force search because you have such high dimensional data or such a large data set to work with. But also that's why neural nets can be overkill for smaller data sets and actually perform less well on smaller data sets than like a linear regression or something. Okay, so what was I gonna say? Backwards through, we need lots of data, I said that. What else did I want to mention? Actually, that might have been it. We talked about moving backward through, oh, right, training examples. That's what I wanted to talk about. So as we move data through, we kind of like move and we feed it a single data element. So think about it like a row, right? We're gonna feed a row of our data through the network. It's called a feed forward. We're gonna feed the network forward, our little row. It's gonna try to make a prediction, and we're going to learn from that outcome, and then we're gonna move backward through the network, just like a wave, like moving forward and then back. We'll back propagate through our network, update the weights and everything to improve our accuracy. And Krieger Sorcerer X, you say often with smaller data sets you can reduce dimensionality. Yes, but often with smaller data sets you don't need a neural net. You don't. Like, I can't tell you how many times I've been brought in to help people out where they have smaller data sets, but they just wanted to build a neural net because neural nets are cool. It's not working, it's not doing well. I literally just replace it with like a 100-line easy linear regression or something, and it outperforms. So that's why I like to start with simple if you can. All right, so our process of backpropagation. Process of backpropagation is going to look like this. Ooh, we haven't used yellow in a while. Let's go back to yellow. It looks so nice with the black background. All right. So we are going to find the error. Not the sum of the squared errors, but the simple error, which is just going to be our we are going to here's where the math comes in. I'm not going to sit here and derive all the math for you. I have a note to do that after this, actually. So hold on. Let me write down the process, and then I'll show you some of the math. We are going to... That's not how you spell that word. Apply the derivative of our activation function. Do I really need to do this right now, or should I show you the math first? Yeah, let me show you the math first, actually, before we do this. I think it'll make more sense. 10 melon bread, thank you for following. Thank you for the nice handwriting. Oh my goodness. Well, I am glad you think my handwriting is nice. I don't often feel like it is. Okay. the math of backpropagation. And this is like math in scare quotes here because I'm not going to go through... Ooh, lag. Math of... Man, that's laggy. All right. I've been having this issue. I like this, and I like the like galaxy pen and stuff, but I do seem to, as stream goes on, have increasing problems with the lag with this whiteboard, so I might be looking for something else. Okay. So, I gotta get my doodles here. Yeah, this is my real handwriting. It's not great. Okay. Alrighty, so let's see here. What did I want to talk about? So let's use a really, really basic neural net because the math is going to be painful. That sounds bad, I guess. All right, so we're gonna use just like one-dimensional kind of thing here. All right, so this is our massive neural net that we're dealing with. We have our input layer, our hidden layer, and our output layer. Right? And layer here is very much, again, in kind of like scare quotes because layers typically have multiple neurons, but we're making the drawing and making the math a little bit easier on me. So, all right. So let's say that we've got our input, and how do I want to do this? So here are our connections. Think about how to draw this. All right. And then we're going to have our first weight and our second weight, easy peasy, right? And then we are going to need a way to refer to what comes out of that process of like multiplying our x by weights and adding the bias. So you'll see this often. I'm going to teach you some of the machine learning notation here, or the neural net notation. Is that this is often referred to as an activation value, and so you'll see it denoted with A. Okay, so we're gonna take this will be our first A, right? This is gonna be A1. This will be A2. Good night, Eric. Thank you for stopping by. Bye bye. And so if we were to define, say A1. What is this actually? A1 is going to be equal to see if I've got this right. Did I count them right? The notation is always the hardest part, honestly. We are going to have from the one before it. So yes, we're going to have weight 1. Actually, let me do the last one. That'll make more sense, and then we'll move backward. Backpropagation, even in our notes. Okay, so A2 is going to be equal to this weight here, weight 1, and we are going to multiply that weight times A1, and we're going to add our bias. So in this case, we're also going to have a bias for each of these. As it moves through there, A2 is equal to yes. Yes, okay. It's just that the 2 and the 1 we're throwing. All right, and so this then gets passed to our, I forgot our activation function. Gets fed into a sigma. Oh, thank you, MH Zenerman. Wasn't looking over at chat for a second. All right. There we go. Hopefully you can see now. So, we take a weight times the output of the previous layer, we add our bias to it, we cram that into our sigmoid function, and we get our output. And so, in this case, of course, our cost function, right, would just be A2 minus whatever our label is squared. So whatever the answer is, instead of label, I'll put answer. Maybe that'll make a little clearer. Answer. or the correct A2 in this case, right? That's going to be our cost. And so when we think about the process as things move through our very, very small neural net, let's think about how we get the cost. Okay, so we've got cost, and I said that's equal to, right? So if we rewrite this slightly differently, actually, it'll be a little bit easier to see. So what do we need to be able to figure out the cost? We need our answer, which is something we're kind of holding back, right? And we also need A2. How do we get A2? Well, I've got it right here. We need, how do we get A2? We need weight 1. We need bias 1. I'll make this. We need the output from the previous layer, and we need bias 1. Okay? How do we get, these are just constants, right? How do we get A1? Well, same thing. We need, in that case, our 0th weight. We need our input, and we need our bias for this. And it goes on and on and on. And so this right here is illustrating why we need backpropagation. Because if our cost function's telling us, hey, you know, your A2 needs to change, well, it's not just a simple matter of tweaking only the weight and the bias associated with moving to that neuron. We have to go backwards through the network and figure out, how does W0 need to change? How does B0 need to change? How do all of these, let's focus on weights even just for now. How do the weights need to change? And so there's something that we've introduced already during this stream that I told you helps us understand how one variable changes because of another one. And do y'all remember what that is? And Kadork123, thank you for following. What's our awesome math thing that we're gonna use? Putting the notes aside for a second. Oh, and I can take a sip of my drink while I'm waiting for you all to answer. You all are teaching for a second. What's the thing that we learned? A derivative, Stannis for King. To the rescue. Yes, derivative being that awesome math tool that we learned that will help us figure out how something changes related to something else. Yay! Thank you so much for the bits, Gamer85. Welcome, welcome. Loafbone, how are the dogs? Because that was 100 bits, and I think they're owed now 3 treats. Wait for Loafbone to let me know if the dogs are available for a brief pause. Give it time, more time? Okay. Giving it 2.5 hours. Hubble's in a bad place. Oh, is he okay? Poor puppies. Is he just sleeping off he's very upset. Why is he upset? Hold on, this might be Sass. Is he very upset because he can't go outside or something? Huh? Oh, right, okay. Well, poor babies. All right. We will let them calm down from the fire alarm incident. They don't like loud noises. It freaks dogs out. So poor dears. Okay. So back to backpropagation. We'll put the treats. We'll keep a tally of treats though. We've got 3 treats banked for the dogs. So don't worry, Gamer85, we will be definitely paying your bits forward to the dogs momentarily. Okay, so derivative, right? Roughly speaking, conceptually speaking, what do we want? We want to understand 2 things. We want to understand the change let's see, how do I want to write this? We want to understand how to change, how our cost function changes, so how our errors change when we change, when the weights change, right? If we understand this very deeply, and if we knew this explicitly, it'd be really easy because we would know exactly how to tune the weights to change the errors. We also, though, because we do have these, the bias, we need to understand how the errors change when the bias changes as well. And let's see, mediocre gamer, fire alarms, fireworks, the male, yeah. Fireworks and storms are bad for both dogs. Hubble really likes fire trucks. He sings to the fire trucks. But fire alarms, neither dog really likes the fire alarms. So, alrighty. And implicit death. Whew, what a name. Thank you for following. Okay. So, if we change this a little bit into some more math language, all right? What this is going to be is this is going to be the delta. It's going to be, how does our error change? How does our cost function change when our weights change? And this is going to be, how does our cost function change when our bias changes? And the reason why I'm using this like weird, like, you know, music note looking symbol, this small delta instead of the letter D, is because these are called partial derivatives. And don't worry so much about it if you haven't done the math, but basically what it's getting at is that if we've got a lot of different variables, it can be really complicated to understand how a function is going to change. So what you do is you kind of hold the rest of the function constant, and you're like, well, if I've got y equals x plus z plus j or something, and these are all variables, and I want to understand how does y change when z changes, I'm going to pretend like x and j are constants. I'm just going to say, let's just see what the effect is if I only change z. And so that's kind of what our partial derivatives are going to help us do, is when we've got these really complicated functions, we can still get our derivatives even if we've got a lot of variables. And Zon Bloop, thank you for following. And so those of you who are, you know, familiar with calculus, this little part here is for you. Don't worry so much if this is not up your alley, all right? You don't need to fully understand this. But rewriting this in math language, we're going to call our cost function C for easiness, and we have our weights W. How does this change? Well, we are going to need to look at, and I rewrote this wrong, didn't I? Because it's stupid. All right. Actually, before I write this out, that's right, I need to, no. Okay. Let's simplify some of the terminology that we've been using. Okay, so what have I shown you? Right, yes, this. Aha. So we have this form, A. You know what A is now. But because all of this is like a lot to write out for the purposes of what I want to do here, we're going to abbreviate this as Z. Okay? Okay. So now we've got A, which is after we've fed things into our activation function. We have Z, which is, you can think of it like our input once we've combined it with a weight and a bias. Okay. So how do we get our cost function then? Well, in that case, what we're going to need is, and I always get these done in the wrong order, so is we're going to need, so instead of equals, little arrow. Okay. C is our cost function. W is our weights. And so what are we going to need for this? We're going to need, how does the cost function change when we change, oh my God, this is the problem with me changing my, the way that I was notating things. I don't want to use Y here. So this is A. So you'll more commonly see A than things like X and Y. So I wanted to make sure that all of you kind of could follow, at least if you read like on another website or you go read a textbook or something, you're going to see things like Z and A. Jay Closer, thank you for following. And all this is really getting at is this is the output of the previous layer, right? Because remember, A is just we've crammed stuff into our sigmoid function. So we're saying to understand how the cost function changes when we change our weights, we need to understand how the cost function changes when I change the previous output. That makes sense. We know that, you know, when we change one layer of our network, those changes affect future layers. And Machine Gun 21K, thank you for following. Okay. And then once we have that, we need to know how does that previous layer change when and then layer. So what was the abbreviation? DC. Yep. And so for this is how does our output change based on input? That's all that means. And then how does that input change based on weights? And even if you just know basic fractions, you can see we would cancel this out, cancel this out, cancel this out, cancel this out, and we would get our how does our cost function change according to weights. And thank you for following Kills McKingston. Similarly here, this is going to be almost the exact same thing. I'm going to use B for our bias. We're going to have the cost function changing again according to the output of the previous layer. How does that output of the previous layer change when we get an input? And then how does that input change based on the bias? Okay, and so this chain rule here and our partial derivatives allow us to figure out the change in cost function when we change our weights, or the change in cost function when we change our biases. And so once we're able to figure out, okay, we know the relationship, now we can exploit it and we can update our weights. And so our weights are going to be equal to our previous weights minus this alpha, which is going to, we'll talk about that in a minute, that's going to be our learning rate, times, you know, oh, that's gross, times the thing we just figured out. Similarly here, biases are updated in the same way. Okay, so I know that's a lot of math. I will also write really quick here so people can follow that A is our sigmoid function with our weights times the A. This is I1 plus our bias. And then, actually, so that this is clearer. Oh no, our music stopped. Hold on. This is our weights times our plus our bias. Okay. And that, where's our music? Start over our music. Oh, here we go. Okay. So, if the math is scary to you, who cares? Don't worry about it. We will figure this out in a different way, sort of. I will basically tell you how to do it. So if you're not ready for the math, please, please, please don't worry. For folks who are interested in the math, I am just going to really quick show you how we would figure out this relationship. So if we're going to use our DCDB, our partial derivative of the cost function with respect to our bias, what we're going to do, did I want to do this? I did want to do this. Okay. Is we first need to remember what our cost function is, right? Which is going to be, okay. So, let's change color. There's too much red. Red is like a scary color. People don't like red, mostly. All right, purple. Purple's happy. Here we go. So, to figure out how our cost function changes when we change our biases, we need to figure out first how our cost function changes when we change our input, or final output, essentially. BH Blue Raven, thank you for following. And so all this is going to be, this is a really easy partial derivative. It's going to look like that. Our next one that we need to know is how does our, our activation function change when we change z? Well, this one's real easy. This is just the derivative of our sigmoid function. So remember, don't be worried about that apostrophe notation. That just means derivative. And for those of you, we will go over the derivative of it later. Actually, I think somebody put it in chat. Yes, MH is a Merriman, exactly. So this is just going to be I did it Z, not X. Oh, the math habits. All right. And what's the last piece of our puzzle? We need this, which is very, very easy. In this case, it is just, we're going to hold the rest of it constant. It's just going to be, well, this is, oh man, I want to do the other one. This one's easy because this is a constant. This is B. They go away. We essentially get 1. Up here, because we're multiplying something by our weights, we hold the rest of this constant. This is just going to be A weights. Goodness. Alrighty. And these are the same. The rest of these are the same. Let's see. Throw some math. Exactly. Yes. I have all your dream jobs. That's awesome. I've liked my jobs. Okay. So again, this is just a tiny, tiny, tiny step into the math of backpropagation. Please don't panic though if you're like, oh God, there's deltas, there's like sigmas, what the actual fuck is going on? Don't worry. It's gone now. Let me see, have I extended too far? Okay, all right, and we are, look at this. Look at this wonderful intro to neural nets. Are you all ready to write some code? Because I think I am. Let's build this thing ourselves. Okay. So many pretty colors, I know, right? I try to make it really nice and colorful. So it's a little more fun that way. All right, so I'm gonna switch here while I get a few things set up. Where did I put it? I'll put it somewhere. There it is. There's our code. All right. That's what we're gonna use. I will move this here. And that's our music. Our music's good. I don't have to restart that for a little bit. I just did that. Okay. All right. I know the backpropagation math is tough. We can do a deep dive into the backpropagation math at another date if folks really want that. But conceptually, before we start to build this in code, how do you all feel about the idea of gradient descent, the idea of it, gradient descent, and backpropagation? And while you're telling me how awesome it all is, I am just going to get our data ready. So this is the Titanic data set we've used in a previous stream, Spacebound Fears. Thank you for following. And I'm just going to repeat the data processing we've done before, dropping some of those labels that we weren't really interested in, turning everything into numbers, doing our dummy variables. So this is just going to make it go a lot faster if I've got our data already ready for us. And I'm putting this in here so all of you will have access to it. Okay. Okay. That's all ready. All right. We're good? Awesome. I am glad to hear it. Okay, so don't worry. Did I zoom in? I didn't zoom in. I even said I was going to zoom in for all of you. All right. Okay, so this should look familiar. None of these steps should be a panic mode. This is all of the stuff that we did previously to our Titanic data set to get it ready for use. So like I mentioned, we're gonna drop our nans. We're gonna drop some of these labels, these features that I don't think are gonna be very useful. They weren't useful for us last time. We are going to get our dummy variables for those features that are categorical. They're non-numerical, so we need to get our one hot encoding going. And we need to scale our data. All of you know that. Scale it, train, test, split it. So all of this at this point, those of you who've been with me since day one, this is old hat to you, okay? This should be easy peasy. Okay, so, I did do it that way. All right, so I did this when I was setting up the code for stream. I first wanted to show you how the various parts will work, but then I wrapped it all in a class because that's going to make it a lot easier for us to use later. So I have to remember really quick how I did this. Okay, so our first step when we're building a neural net is it's almost like when you're driving down the road and you see a construction company that has started work on a big office building. And the office building isn't finished, the windows aren't there, like the walls aren't there, but kind of the skeleton of it is there. You can see the shape of it. You can see how wide it's gonna be. You can see how tall it's gonna be. You can see how many floors it's gonna have. Similarly, our first step here is we have to build the skeleton. We have to build the architecture, okay? So let's just call this create network structure, all right? And in order to do that, we're gonna need a couple of things. We're gonna need the number of features that we're going to be inputting so that our neural net knows how many nodes it needs, how many neurons it needs in its first layer. We're gonna ask it how many hidden layers. We need to tell it how many hidden layers we want. And then, do we need that yet? No. We need to know what the expected output is gonna be, okay? And so, I believe I just turned this into a list, didn't I? Yeah, so we'll be giving ourselves back a list here. All right, really, really basic. And I guess I should put that caveat out there for all of you. Folks who might come into the chat and you have more experience with machine learning or more experience with neural nets, that's great. I don't recommend building it by yourselves. I don't recommend doing it all from scratch. That's what we have wonderful libraries for. But in this case, the process is going to be more valuable than the outcome. So the act of building it ourselves will be very informative. So that's why we're not using like TensorFlow or Keras or something tonight. And Somniactic, thank you for following. Let's see. That's done. All right. So to create our network structure, what do we need? We need and we're gonna, again, very, very, very simple structure here. So we are going to assume, unlike some of the drawings that I've done, we're gonna assume that our input layer and our hidden layers are gonna have the same size, just for the ease of conceptualization. So we're gonna call these our layers, all right? And to build our layers, think about it, we need those neurons. And what are our neurons? Our neurons right now are going to be weights and biases. And yes, TensorFlow and or Keras and or probably not PyTorch will probably be used later in the series. I haven't decided what libraries I'm using for some of the later streams, But yes, I'm not going to build things from scratch every time. Good God, no. I'm only doing it this time for all of you so that you have this experience. Okay. So for ease, one of the like kind of sleight hand tricks that we're going to do is instead of having our weights and our biases be separate variables, I'm going to store the weights in a list or in a one-dimensional array, and the last one in the array is going to be the bias. So we'll just use up until the last one is weights, and then we'll just use the last one as a bias, and that's just going to make it a simpler thing to code. Okay, so we're going to have our weights, and our weights, as we talked about earlier, just like in reinforcement learning, when we're first starting out, just like with those Q values where we kind of initialize them all as 0 and we just picked random stuff to do, our very first step is going to be, we're going to pick random weights. That means our neural net is going to be really, really bad at first, but that's okay because it's going to learn. We need to start somewhere. So, did I do all my imports? Yes, I did. Okay. So we are going to oh no, I haven't done the class yet. So we're going to call this n input, right? So we need as many weights as we have inputs, right? Because each of our neurons needs a weight. This is non-inclusive, so we have to add 1. All right. So what this is going to do is this is going to give us all but the last layer. So we're going to have little dictionaries for each layer, and that dictionary for now is just going to contain weights, the length of our features for now. And we need an output layer. Which is going to look very similar. It'll also be random. How did I do this? Right. And then I should probably do this. Yeah, that's fine. In range. This is our N output, is what I called it. Right. And then our network is going to be this list. Our network. Oh. Actually, now that I'm not using the blackboard, I can move my... This is where it's a little bit more comfortable. All right. And then... Okay, so let's see what this looks like. Let's say I'm gonna give it 10 features, and I want 2 layers, and I want, well, we're talking tonight about binary classification, so I want this to be, all right, boom, done, right? There we go, we've built our neural net. Now, it's gonna be a little bit more complicated, but you can see that we have some of the structure already built in. So we have our 2 output neurons. We have our, well, these are 2 output, yes, each with weights. And then here is 1 layer, and here is our 2nd layer. Okay, easy peasy, right? This should be good. All right. So, oh my God, should have broken this up a little bit more. I'm trying to remember what I need to do next. Let's see. That'll work. D2050. Thank you for following. All right, easy. Are we done? No, because we don't have any of the things that, we have no way to train this. We have no way to, update our weights. And hi, D2050, or 200,050. I'll just call you D2000. Welcome. I'm glad you're here. Okay, so we also need a way to process our inputs, right? So we need to be able to multiply them by weights, and we need to be able to add our biases, right? So let's define a function that we're going to use to process our inputs. In this case, our inputs are going to be a list or a one-dimensional array, and our weights are going to be a list as well. And we need to convert this into a float that we can then feed to our sigmoid activation function. Okay, so first thing we need to do is we need to multiply our weights times our inputs. And there we go. All right, why am I doing weights? Why am I doing the range of weights minus 1? Who's been paying attention, class? Teasing, of course. If you all are lost, I will explain. But why are we not zero indexing? Define null zero, but that is always a good guess. Bias last. UZ, me now, coming in with the answer. Thank you, friend. Excellent. You are 100% right. Like I mentioned earlier, for simplicity, we are going to be having our weights be the first n-1 members of our array, and then the nth member, the final member of our array, is going to be our bias. So exactly. So in this case, we will, once we've processed it, that last member is going to be our bias, and we're going to add that to the sum of our weights times our inputs, and we'll give ourselves that. Okay. So we also need an activation function, right? So we're going to need to take in our processed input, right, which is going to be that float, and our activation function here is 1 over it's just our sigmoid function. We looked at this earlier. And oh no, you're asking what the question was. The question was why here we were only indexing to the second to last member of our weights array. Okay. What's our first step here? We have our activation function, we have a way of processing inputs, and we have our neural net structure. What is our first step? Yes, that'll work. I can put this away. Just cleaning up my desk. So we actually, MH Zinnerman, we already have initialized our weights. We have random weights to start out with. Yes. Got some tea so I don't lose my voice. We've initialized our weights. We have the functions in place to process our inputs and pass them to an activation function. So what do we need to do? Ooh, hot. Before we even cover error, before we even get to error, we need something to compare with our labels. How do we get that? Thank you, Loafbone. Your contribution is tea is hot. Yes, I appreciate it. So we'll need to initialize an X and Y. We already have them. So I'm already using, we've already got our Titanic data set prepped and everything. So we don't need to simulate X and Y here. We've got data, but what is the process? Like, we've got the structure, like we've got the drawing, we've got our data. To calculate an error, we need outputs. How do we get outputs? That's the question. Ooh, mediocre gamer, you asking me about iced tea. I really don't like sweet tea. Sorry. I don't like very sweet things. So... All right, if we are still stuck, that is totally fine. So this is what we talked about earlier, which is called feed forward, right? So this is where we're going to do a forward pass through our neural net, okay? So in order to do that, we need our network, right? Which is gonna just be that list. We are gonna need our inputs, which is also gonna be a list. Okay. And so how do we feed forward? Well, for each layer in our network, what do we need to do? So think back again to the, like, maybe I can pull up the whiteboard and zoom in at least on a picture of a network. So if you need the visualization, you can have it. This, I know my drawings are really bad, but hopefully at least having a little bit of the visualization might be helpful. Sure, this just me. Okay, there we go. And thank you so much for following Thomex. Tomex, welcome. This one. And Vinahora, thank you for following. And so using me now, you say, is processed input and processed the same in the activation function? Yes, that was me forgetting to write the rest of this. Thank you for the catch. And Pavan GC, thank you for following as well. Okay, so for each layer in our network, what do we need to do? How do we pass data through our network? I know it's hard. It's like you learn the conceptual, even the mathematical approaches, and then when you sit down here and you got to go, how does this actually work? It's a little more challenging. But that's really why I wanted to do this, build it from scratch, because I think it forces you to really understand how all of this works. And Nordovich, thank you for following. Jane 808, you say scalar product, right? Scalar product. No, of what? Okay, so we need to process our inputs. Yes. All right. So we'll need a way to store outputs, so I'll just get that ready. And then for each neuron in our layer, right, we need to, remember Z is just the input times the weight plus the bias. So that's just going to be our process inputs. And so for that, we are going to need, how did I do this? Inputs, got our inputs, and then our weights. Okay. And then our output, which we're going to store, is going to be our activation function. Once we process those inputs, we got to pass that. Yeah, Jan, there we go, dot product. Once we have processed our inputs, we've multiplied them by the weights and added the bias. It helps if I spell function correctly. We need to pass it to our activation function. And, okay. And then we are just going to add this to our list of outputs. And then our inputs become the outputs of the previous layer. Easy, right? So let's think about this conceptually, make sure we understand what's going on. For each layer in our network, there are going to be outputs. For each neuron in our layer, we need to multiply the input times a weight at a bias, feed it to our activation function, and record that output so it then can be passed to the next layer of our network. There we go. Not that many lines of code for a feed, forward, pass. So let's make sure this works, right? We'll call this neural net. And let's pass it. What did I call it? Let us pass this 0, and we'll just pass this. Yep, all right. It's gonna be just, we're gonna practice, just see, make sure that this works. Of course it doesn't. Process is not defined, because I'm a dork weasel and I named something wrong. I might have just forgotten to refresh that, which somebody already caught me on because they're awesome. Using me now, that was you, thank you. There we go, done, right? Okay, easy peasy. OG Quiche, thank you for following. And Ulrich's Wrath, thank you for following as well. Clyde's gonna say dork weasels are the best weasels. Well, I hope so, because I'm definitely, that is me very frequently. Okay, and KC3, your name's gonna kill me here. Sorry, I'll call you KC3. You ask, what am I building? We are building a neural net from scratch, so from the ground up. So we've talked for the last 3 hours about neural net architecture. What is a neural net? What's a neuron? What's a layer? What's an activation function? And yeah, virtual assistant, this is gonna be, well, it's gonna be like 2 layers. We can make it as many layers as we want, but it's gonna be a basic perceptron neural net. Because that's really the example that we've been using throughout all of the notes. And so I think it's gonna, rather than throw you curveballs, change our activation function and everything, I think it's, for consistency's sake, this is what we're gonna build. It's also the easiest to build, especially for your first neural net. The activation function crystal coder is just sigmoid. It's just sigmoid function. And so, basic, really easy. Yes, Stan is working. You ask, am I an engineer yet? Yes, there you go. And so we have feed forward. All right, easy peasy. Are we done yet? No, sorry, we're not done yet. What is our next, what's our next step here? And Curtis C. Wright, thank you for following. Are sigmoid functions considered old? I guess I'm old then. Sad face. Let's see, and what are autoencoders? Well, we'll talk about those probably when I do natural language processing, which is day 11, if I remember right. Schedule. There we go, perfect, all right. And so, oh, love bone. Duplicated. And is there source material you're working out of? Not really. This is a combination of like what's in my head, what's in some textbooks. There's a lot of articles online that you can read for like ideas for how to start this. Generally speaking, when you learn about neural nets and you start using them, you don't build your own. I think it's like a really good learning exercise because it's like by making yourself build it, you understand a lot more what's going on to debug things. You've got to figure out why it's being awful. This is not, the neural net that we're going to be building tonight is not designed to be the most accurate, cutting edge, predictive tool. We are building it so that we understand deeply how all of these different pieces fit together. And Goofy Lagrangian, you say, can I use the code on GitHub in the Colab? I've actually never used Google Colab, I'm sorry. You say, will it run or do I need to include some other packages? You'll have to have the basics, like the basic, like data science packages installed. So like, I think Python comes with NumPy, now NumPy. I think we've used Matplotlib, scikit-learn, pandas. I'm trying to remember what else we've used. I would say if you just like the basics essentially. And Joe, not Joseph. Well, welcome, Joe. And thank you for following. Okay, what comes next? We've feed forwarded through our neural net. What do we do next? And MH Zanarman, you have a slightly off-topic question. So while everyone else is answering my question, I will read your question. You say, before you end stream, the question if possible, you have an idea to de-blend galactic pictures where there are two galaxies in the picture overlapping using independent component analysis I see on the XY plane. Do you also do research? I've done some machine learning applied to astrophysics. And Galaxy Zoo is great. Lots of good stuff there. Oh my goodness. Thank you, Zalbag, for subscribing. Thank you for supporting the stream. I appreciate it. I've been putting a lot of hard work into this, especially this stream, this particular one, the neural nets one. So thank you. I really appreciate it. It means a lot. And KC3 and the Lazy Fish, thank you so much for following as well. And Goofy Lagrangian, I'll get you like a requirements.txt file after this, and I'll add it on GitHub. I'll do backpropagation. Exactly. And so to do backpropagation, right? We first have to do what? What is our first step in backpropagation? And no problem, Zalbag. I'm glad you are enjoying this. And I'm the gingerbread man, and I think I said the lazy fish already, welcome, but still welcome again, I guess. And I'm the gingerbread man. Thank you for following. All right, so in order to do backpropagation, remember when I was talking about, yes, I know, the two complex like terminology things we learned tonight. And I said one tells you what needs to be changed, the other tells you how. So we need the what. And so for that, we're going to need to figure out our errors and propagate them. Okay? And so for that, we're going to need our why. Whatever we know our labels to be. And Severo, thank you for the bits. Cheers, my friend. Okay. I'm having to like look. So finally what I'm going to do is once we're done with all our definitions and we've got this stuff all done, we're going to put it into a class. And as I was, prepping the code for this stream and making sure it was going to work and tweaking it and everything and making sure like the variables were named really clearly and not lazily like I tend to do, I put everything in the class. And I didn't think to also have notes for myself on what order I did them all in. So I'm also trying to like double check and make sure, okay, I did this. This is good, right? Fine. Don't put self in everything. So if someone catch me if an errant, a wayward self makes it through. And Goofy Lagrangian, you say, out of curiosity, who was my Enceladus? As in, where did I learn this stuff from? Where did I learn this stuff from? By stuff, what exactly do you mean? So are you talking about data science as a whole? Are you talking about neural nets specifically? There's actually a really good online book. Oh God, I'm so bad with names. So give me 1 second. What is it called? I'm a bad human. This one. Yes. What is this person's name? So I can give them like a Nielsen, that's right. So Nielsen has a great online, free, but please, if you're able to afford it, throw some donations as always. Those of us who do things for free, we like doing them for free, but tips are always wonderful. They pay for the coffee, they pay for the tea, they pay for the alcoholic beverages. And that is a great online book that goes into quite a bit when it comes to neural nets. And let's see. Oh, the Nielsen of quantum computing. I actually don't know. That's been on my list of things to like learn more deeply about, and I have not been I've not been doing that yet. I've been focusing on my time on you all, so that's fine. All right. Propagating errors. How are we going to go about propagating our errors? Well, first of all, it's called backpropagation. So we're not going to go, we've fed forward through our network. And now we need to move in reverse. function annotation here. All right. Okay, so we're moving backwards. Alrighty. What do we do when we move backwards? Well, we're going to need a couple of things. The layer that we're going to be looking at is, you know, whatever the layer it is that we're looking at, whatever's at our index, and we need to keep track of our errors, plural. And what's nerdy galaxy shit? Did I miss something? Loafbone, you say Jess has worked closely with Galaxy Zoo previously. She's done joint stream with another astrophysicist. Yes, Brooke. Okay, so you can follow her on Twitter. She's really, really cool. So she was my research mentor, and we streamed a little bit together. Hopefully we're going to do future streams as well. But awesome, awesome, awesome. She studies the relationship between the evolution of host galaxies and their supermassive black holes. So she's awesome. Probably one of the coolest people I've ever met in my life. Also just like a good person, where you're like, you're really, really smart, and you're a good person, and you're really nice, and you're a good teacher. Like, are you serial killer? Like, people like that, it just, sometimes there are those like gems of people, and she's a gem. Okay. So, let's see here. What are we doing? All right, so how do I want to do this? How did I do this? Yes, that's right. So if we're on our last layer, it's going to be a little bit different, right? Because we're outputting things. So if this is basically saying if we're in our output layer, we're going to go through. We're going to go through each of our neurons, okay? So we're going to iterate through our neurons, and we're just going to compare, what we thought it should be with what we got. Because with our last layer, we actually have the ground truth that we can compare to. With other layers, we won't, right? So right now, all we can do is for our last layer, we want to compare to those labels that we have. And Fobden Masood, you say, what would be your advice for a software engineer who wants to learn machine learning? Well, what languages do you know? Because software engineering is such a broad field. I would say that, it's great to come in with a knowledge of programming. That's going to help immensely. The biggest things that are going to trip you up are going to be the math, then. The math and the statistics. So rather than worrying about knowing what libraries to use or, how to do stuff in the cloud or whatever. Good. Okay. Python is very, very, very common in machine learning, so you're fine. I would instead focus on enriching your knowledge of math. So improving your statistics, brushing up on your calculus. And once you feel like you've got a solid, handle on your statistics and your math, then you can start looking into more machine learning. And Fruit de Dude, hi, welcome. I don't know who Judy is from Cyberpunk 2077, but I'm going to take that as a compliment. Hopefully it's a compliment. That's fine. Even if Judy's like a giant cyborg dragon or something, like I'll embrace that too. That's fine. Okay. So, propagating errors, right? We have figured out our errors for if it's our output layer. Otherwise, an Netalosk, thank you for following. And then Jacob Shrimp, you said the actual fun you had with training stuff in Unity game engine. Ooh, yeah. Okay, so I'm actually learning Unity. I put it on pause to do these 12 days of machine learning. But my typical stream schedule is me learning game dev with Unity and C# on Thursdays. And so I'm hoping to get there so I can actually kind of smoosh the two things I love, video games and machine learning, into one happy little package. So, Goofy Lagrangian, you said the Nielsen book you mentioned, the codes are in, Python too? I don't know. Python, I wouldn't read that to copy code. I would read that to understand the math and the concepts and then go and do the code yourself. And fruit the dude, we are building this is like baby's first neural net. It's building our own neural net from the ground up, from scratch. We're not using any libraries apart from, you know, NumPy, of course. All right, my dears. So we got our output layer errors. Now we need all the other layers, our hidden layers. Okay. So again, in this case, we don't have a list of errors because these aren't our output labels. We are instead going to have the next layer. One layer forward. What is the title of that Nielsen book? There you go, my friend. There you go, Lobo Capablanca. I don't remember the exact name of it, but that's the link to it. So it looks like, if I'm just reading the URL, it is neural networks and deep learning. So, all right. So let's think about how we want to do this. Right, because we're backpropagating, or not doing full backpropagation yet, but we're propagating our errors backward through the network. And so we need to reference one layer forward of where we are to be able to figure out what our errors are now. And yes, Lord Alpaca 666, I am doing a feed forward and backpropagation network by hand in Python. We also did 3 hours of neural net math and the basics, at least, of neural net concepts and math before this, so everyone would be prepared to build it. Right. I'm so glad I have the notes, honestly, because if I didn't have the notes, that would be tough. Because I get distracted by chat. You all are wonderful. I love answering your questions, but this is why I sit down and I have all the notes, because I'll get distracted, and it's like when I'm coding for work, I'll be so into it. I'm like really excited. I've got like 5 different things I'm holding in my head that I'm like, okay, I got to do this next, and then look at this, and like I'm just in the zone. It's like feels like the Matrix. And then like my dog will come up and like bark at me or like nudge me or something, and I look down just to pet him because he's extremely cute. And then I look back, I'm like, what was I doing? What? And it takes me forever just to get back on task. So, whew, I'm feeling grateful for the notes tonight, for sure. Yes, Lord Alpaca, please share your video of a neural network simulator. That sounds really cool. And Enk4Y, thank you for following. And Loafbone, will you check the video out for me? Let's see here. Error, and then we're going to append our errors. Or no, we don't. No. Yes. There we go. So then we've added up. Yep, okay. Oof, all the layers. Am I right? Haha. Okay, so now that we have errors for each of our layers. JK, it's safe. Okay, all right, cool. Just gotta make sure I'm not gonna like accidentally bring up something really inappropriate. Especially now that I'm on a... Do I have the permission to put... Like, this is on YouTube, so I get really worried now. Because I've already had a copyright BS happen. Oh, this is neat. I love visualizations of neural nets. Yes! This makes me so happy. I like being able to like see what it looks like, you know? I know it's not YouTube. I mean my VODs. Yeah, okay, well, yes, I will ignore you. See, friends, things get complicated. Look at each of those connections, right? I was drawing very, very simple neural nets for you. Like baby neural nets. But you can see very quickly how this gets complicated, right? And Yassine 10K, thank you for following. It's like what I was drawing. Yeah, this is like, I wasn't just drawing things to make myself happy. Like, I was giving you accurate representation, very simple ones so that I didn't have to draw that. But yeah. And you can see the errors also being tracked, which is cool. This is super, super helpful to visualize. What? Why do you have a... Oh, okay, I see. Oh, this is neat. This is really cool. How did you build this? I was trying little like, very basic. Ah, you see the A, right? I was teaching you the right letters. Or no, that might be a sigma. I can't tell. That's really cool. No, this is super, super neat. So I'm so glad you posted this in chat. Thank you. We can go back to the easy stuff. Don't worry, Onad. We're back to the easy stuff. Our happy little, neural network. Okay, so we have figured out, we've gone through our output layer. We've gone through all of our hidden layers. We have figured out our errors. Okay, so yes. What do I want to do here? Yes, that's right. Okay. Oh, we need something for this. Crap on a bucket. Hold on. All right. I'm gonna type it out. Don't worry yet. We haven't done that yet. So, right, we gotta remember how when we were doing our backpropagation math, we need the derivative of the activation function. Well, we're gonna need to define that. What did I call this? Yeah, activation derivative. All right. Really, really easy though, if you remember. It's gonna take that processed input, and it's gonna output a flute. All right, and it's gonna be very, very easy. What did I call this? Activation function. All right. So if I spell things right. Okay. So now this won't, we needed that, and I forgot to define it. Right, because in this case, we haven't made this into a class yet. Okay. All right. So we have propagated our errors through our network, and now we need to change our weights, right? That's the other part of backpropagation. The first step is figuring out what the problem is, and the second step is figuring out how we have to fix it. So let's backpropagate. Yes. Whew. All right. Badger Hell, thank you for following. All right. So, I think we should turn this. I'm thinking about when to do this. All systems go. Thank you for following. All right. You know what? At this point, really, we've tested out our feed forward. We know we get some outputs. We know at least the code works, right? Let's put this in order. Support people following. Don't freak. Let's turn this into a class so that I can not have to deal with figuring out what all the outputs of this stuff is and like feeding it in and everything. Lujar and Flashy Sing, thank you so much for following. All right, so this is just our basic, we're gonna just have a really basic neural net, all right? And so what are we gonna need in order to have our neural net? We're gonna need to know, just like before, we're gonna need to know our input shape, we're gonna need to know the number of layers we want, and we're gonna need to know, at least for now, this is all we're gonna need to know, the output shape. So let's just, you know, get this all set up. Output. Okay. Yes, we're not ready for that yet. Okay. And so I'm just gonna take what we did up here with our network structure, our processing inputs, our activation function, and I'm just gonna put it into our class, okay? In particular, I'm going to copy and paste this because I promise you this is what we were just doing, but I really don't want to risk accidentally forgetting like a self or something and having this bork itself while we're working with it. Okay, so that should be fine. You love Hubble. Yay, 300 bits for Hubble. I like it. All right, so now we can do our backpropagation because I don't want to sit here and deal with having to hold all that stuff and feed it into a new function. So let's do our backpropagation. How's he doing? Hold on, we need to see how Hubble's doing. And XF83, thank you for following. Oh, baby boy. Little bean. Hubble. Has he calmed down at all from the fire alarm? He looks so distressed. Okay, all right. I hate when he makes those like sad eyes. Poor little bean. He probably just doesn't like the fact you're taking a picture of him, but still. Good. You gave him the trazodone? All right. Poor bean. A raid? Hi, raiders. Hi, thank you, Last Miles, for the raid, and welcome, friends. Hi, everyone. Tonight we are doing, as I've described it, baby's first neural net. So we are building a neural net, feed forward and backpropagation from scratch in Python. We have covered the gentle math and structure of neural nets with pretty galaxy-themed pens. And now we've moved on to the fun bit, which is building it. So so Last Miles did not watch Star Trek on his stream tonight. He remained sober. That's good. All right, you've got a far greater chance of understanding neural nets if you have a little bit of sobriety. So, and Biotechnic, you say trazodone sucks. Well, both me and my dog use it, so you know what? We're fans, at least for now. And Carlos Emmanuel Martin, you say, Dennis wanted me to know that he has no clue, but he said it with more flowery language. Well, that sounds very much like Dennis. And no worries, it's okay. Like, if you are interested, perchance, in machine learning, I would very much recommend checking out the schedule of the 12 days of machine learning miss. If there's something on there that you're like, oh crap, I missed days 1 through 7, you can check out the VODs on YouTube, and all of the code is available along with the notes from days 4 onward. I have to go back, rewatch the VODs and type or write the notes up for you. But days 4 and onward, you will have the Blackboard notes all on GitHub. So if you're like, oh God, you've stumbled into the tough part, don't worry. There's lots and lots of resources for you to get caught up, or if you already know a bit about machine learning and you just want to do a deep dive in a topic you really like, check it out. I'm particularly excited about reinforcement learning. So our last stream was really, really cool. I love reinforcement learning. So I'm also extra excited for Monday's stream, where we're going to be smushing all of the things we learned about neural nets today with the things we learned about reinforcement learning and talking about Q networks. So I'm really excited because I love reinforcement learning so much. But tonight, like I said, this is Neural Nets 101, a soft introduction to neural nets. I've shown some of the math, but if you don't know calculus, don't fear. I also did a conceptual explanation as well. So have no fear. You will be able to follow regardless, I think, of your math proficiency. There's more math for those who like the math. There's concepts for those who don't. And Off Kilter 5280. I don't know if I said thank you for following. I'm sorry if I missed your follow. And Eve. Thank you for following. All right. Okay, my dears. So we have figured out our errors. We propagated our errors, but we have to finish our backpropagation because the second step of backpropagation is changing our weights. Okay, so for this, we are going to need, I really want to change this. I like this being Y. La 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 la. All right, yep, okay. I think that makes more sense. List. Yes, please. All right, we are good. I am using self. Oh, Techrific, if you stepped away for a second, we have moved to the, we are going to turn this into, we're going to turn this into a class. So we have turned our definitions that we use to kind of get our feet under us, figure out how we initialize our network. We're turning it into a class now because I'm tired of dealing with a bunch of functions. It's so much neater in a class. All right, so what do we need to do here? We need to ensure that we have propagated our errors. So that is our first step. Yes. And you, thank you for following. No, Techrific, thank you. You know what? I can't tell you how many times I have a typo or I goof something or I forget something on stream. Because talking and coding and talking and explaining, it's a juggle. So I appreciate any attempt to help make sure I'm not screwing it up. And MacroShe11, MacroShell, thank you for following. And yeah, like I said, so really quick for the new friends, I really would check out VODs and stuff if you are interested in machine learning. The Bojan Ninja, thank you for following. The 12 Days of Machine Learning Miss has been this absolute blast of a series of streams. Well, it's been a blast for me. Hopefully it's been a blast for all of you. Took 2 weeks off work and was like, yeah, let's just do 12 days of machine learning. So I'm trying to take you basically from zero to neural net hero and everything in between. Kakamuza, thank you for following. So hopefully there are some topics in there for you, or if there are areas of interest that we're not covering, be sure to join the Discord, reach out, because post 12 Days of Machine Learning Miss, I will be starting Math Mondays. And I'm thinking about making it like Math and Machine Learning Mondays so we can kind of do a little bit of both. But if there are topics, we also have a wonderful area to talk about papers. If you want to talk about papers or bring something up that you need help with, yeah, come hang out. All right. So what do we need to do here? All right. Again, if we're in our first layer, it's going to be a little bit different. And Crash35, thank you for following. If we're in our first layer, our inputs are really easy. Our inputs are just the instance, our instance of our data set, right? So the row that we're passing to our neural net. And oh my God, it's Chapboy B. Thank you for following as well. Okay, so those will be our inputs. Otherwise, our inputs are going to be, it's really easy, right? The outputs of the previous layer. That's all this is. So just like with the backpropagation, right? We had to look forward one. Here we're looking back one. And Bojan Ninja, thank you so much for hosting. Thank you, I appreciate it. And to all of you also in chat hanging out, I appreciate your company. And hopefully you're learning something. Kaitas, thank you for following. Okay. So we figured out what our inputs are. And now that we have our inputs, I am using I. And then each of our inputs, which might be the output of the previous layer or just the inputs we're feeding it from our wonderful row of our data set. And Mitch's Workshop and Super Radiance, thank you so much for following. Welcome to the stream. We need our weights. And we got to change our weights. So remember, We forgot something. I forgot something. So, do you remember? Probably not, so let's refresh. So, remember here, I'll move that, how I was talking about the rule for how we're going to update our weights and biases, right? I said, we're going to change them, and there's going to be this alpha thing. And I said, don't worry about it. Well, now let's talk about alpha. Alpha is something called our learning rate. And our learning rate kind of represents how much, just like if you remember from the reinforcement learning stream, where we had to decide how much we wanted to change those Q values, right? Kind of similar to this. How drastically do we want to change our weights? And Biotechnic, thank you for following. In particular, if we make our learning rate too high, so like in the reinforcement learning example, if we made our learning rate too high, we didn't have any memory. We were just overwriting our Q values every time. Kind of similarly, if we make our learning rate too high here, we have what's called premature convergence, which basically just means we're finding the fastest outcome, but not necessarily the best outcome. So it's, again, like with a lot of things in hyperparameter tuning, it's going to be a balance. So now we're going to need to make sure that we give it a learning rate. Okay, so now in our backpropagation, we're going to be using that learning rate because as we update, let's make this wider so you guys can see. All right, as we are updating our weights, we need to have that learning rate so that we're not just completely replacing them. We are tweaking them. Like you can think of it like I don't know if any of you play a string instrument. I've got like my violin over there. And when I'm tuning it, I have the pegs, which make drastic changes in the tuning. And then, at least for one of the strings, I have like a little kind of gear dial thing at the bottom. And that one I can do fine tuning, right? And fine tuning is really what we're looking to do with our weights. If we're too drastic, just like with the step size metaphor that I was using earlier, we can overshoot. And so right now, we're going to keep a reasonable, balanced learning rate, so that we're not just looking for the quickest answer. We're looking for the best answer. And what is best? What is this poll, loved one? Dogs, cats, and Linux. What kind of poll is that? Okay, whatever. I trust you. You're the mod. You do your poll stuff. Whatever mods do. Polling the people, polling the populace. All right. Woolsock 007. Thank you for following. Oh no, what happened? Hold on. Yes, is Linux winning? Sorry. It's hysterical. All right. Okay. So now let's see. It's exactly what we talked about earlier. Yes. And similarly, remember that our last member of our weights array is the bias. So we're going to update this differently, just like we talked about when we did all of that wonderful calculus, right? Looks a little bit different. Okay. Hi, Woolsock. Welcome. Okay. So now we have a way of backpropagating our errors. And so lastly, well, not lastly, but almost lastly, let's train. Let's train our network. So what are we going to need for that? We're going to need some training data. And we're going to need the number of epochs that we want to train over. And so for each epoch, no, we're not doing any kind of mini batch learning or anything like that. This is not stochastic gradient descent. We are just brute forcing this. And you'll see how badly it's going to do. It's going to be a dumpster fire. But that's okay because we're not trying to build the world's best neural net. We're just trying to build our first neural net. And so we're not overly concerned about it being the most beautiful thing in the history of the world. All right, sum of squared errors. And then for each of our instances in our training data, we are going to have an input. And then we are going to have, how do I do this? We're going to have outputs, right? So this is our predictions. Right? We're just going to pass our inputs through that network. We did this already. We made a sample, some fake data, and we passed, well, it wasn't even fake data. We just passed a single instance through. And then how do I want to do this? Actually, I'm going to change this. Instead of outputs, let's call this our prediction. So I can make this y actual and it'll make a little bit more sense. All right. And I'll explain this momentarily. Just give me a second. Okay. So the way that our neural net's going to work is a little bit different from when we were doing logistic regression. And we had this like one output value that based on whether or not it met a threshold, we assigned a class, a classification, right? Here we're just going to use the raw outputs from the neural net. So there's going to be 2 neurons. Each neuron represents the likelihood of a particular label. And so for our Titanic data set, we're talking about did you die or did you survive? And so we're going to have, instead of having one that is 0 to 1, we're going to have 2, one representing the likelihood that someone died, the other representing the likelihood or confidence that somebody survived. And so for that reason, we need two possible outcomes here. And of our 2 possible outcomes, the correct answer, our label, is going to be labeled 1. We're not going to do that yet, Strawberry Jesus. And McChillin20 say, every time I see your stream, I just want to start coding. Yes, that makes me happy. Awesome. You should start coding. Coding's a blast. I can't do like the 12 days of Python-ness because the holidays are over. But maybe I can come up with an excuse to do a series of intros to Python if that's something interesting. Okay. Now, how bad did we screw up? Oh, this is going to be so much fun. I can't wait. I love how terribly this does. The Pythonathon? Yes, Onat, I love that. Oh, Pythonic Easter. I also like that too. The Pythonathon makes me... Pythonathon makes me just think of the Parthenon. The Ides of Python. That could be something in March. Celebrating my birthday. I don't want to think about that. I'm going to feel old. The Ides of Python I could do maybe. That'd be fun. Okay, so we need our errors. Our errors, some of our squared errors in this case. And so we're going to have our actual... I goofed it. Hold on. Hold, please. I have a memory of writing something that is incorrect. Hold, please. Where was I propagating the errors? Here we go. No, I didn't do it wrong. Never mind. Yeah, that's right. Right? Okay, I imagined it. Cool. All right. It's always good to check yourself, I guess. The Python strikes back. I like it. All right. You all have to come into the Discord and help me name things because I have many deficiencies. One of my many deficiencies is I literally cannot name things effectively. I suck at titles. I suck at nicknames or names for things in general, usernames, clever name. I'm just like, that is a layer of wit I do not have. So I'll have to crowdsource future stream names. And Mascarian, thank you for following. Okay, my friends. We are doing errors, so it is the difference between the actual and what we have predicted. And all of that because we're doing the squared errors. Yep, that looks good. Now that we have our errors, we need to backprop. And we need to use our actual. There we go. Minger1, thank you for following. No, but, okay, I really like Linux, but Thanksgiving's my favorite. That makes me a little bit sad. Okay, fine. See how it is. All right. Yeah, you ready for this? I'm so excited. All right. So, I like to name, so when I'm like testing stuff out and I'm just making sure things are working, I like to name my neural nets really obnoxious things. So like the neural nets from when I was testing this were Bob, I think I had Frank, I had Carrie. So I will let chat, what should we name our neural net? What obnoxious name should we name our neural net? Alice? Clumsy Net, Linux. We're not naming it Linux. Neural Ned. Ooh, I like Ned. Ned is good. Let's name it Ned. Okay. Did I lose my thing? No, I didn't. All right. And Macroshi asks, what GPU do I have for training the neural net? Oh no, we're not using GPUs. Not yet. This is really basic. So this is just a simple feed-forward perceptron, like single layer or 2-layer network. So we are not, we're not doing, this is basic as hell. Nothing fancy yet. Okay. So what did we said we're gonna call it? Neural net Ned. Right? Neural net Ned is gonna be a neural net. And we are going to have, well, hold on, let me see here. Training data. Did I prep this already? I did. Oh, good job, B. All right, so we need to feed it. That's not what I want. I was gonna say, I'm missing something. Hold on. I called it training data, didn't I? Yes, I did. There we go. Apple 2 Games. Thank you for following. Okay, Apple 2 Games. You say, slow kid just joined. What is our goal? No, there's no slowness. Slowness is a myth. Slow and steady wins the race. What is our goal? Our goal here is to build a basic, functional, feed-forward, single-layer perceptron network. Well, yes, single hidden layer. And the goal is to understand the basic components and relationships in a neural net. We're not at the point where we're trying to create something that is going to be super effective. Because really what I was hoping to do with this stream, kind of a neural nets 101, is so that people will leave this understanding what artificial neurons are, how weights and biases work in a neural network, what the layers are like, what feed forward means and what that process looks like, and the process of gradient descent and backpropagation as well. And so this is the let's, define our terms, understand the basics so that when we come back on Monday and we're going to apply everything we've learned about neural nets to reinforcement learning, it's not going to be a dumpster fire. So, Christian Del Kid, thank you for following. All right. That's right. Called it training data. And we're gonna feed this our number of features. Half Aiden, thank you for following. And I want 2 layers I know it's binary, so we have 2 outputs. And our learning rate, being a little aggressive. Let's see what it does. All right, neural net Ned. What does your network look like? And Apple II Games, you say you're Googling in another window right now. What data are you training on? This is gonna just be the Titanic data set. So really easy, simple, very clean data set, easy to use for machine learning. This is not a good data set for neural nets in particular because it's smaller, but that means it's gonna be fast. And so for doing a very basic neural net, getting that responsivity is gonna be a little bit more important than getting a result. And Coot4, thank you for following. And MH Zanerman, you said where the code does backprop. Our code does backprop here. So first we calculate all of our errors, and this is the beauty right here. We are going backwards, updating our weights and our biases based on the errors. I'm glad, Coot4, thank you. I'm glad for the follow. And like I've mentioned earlier to folks, if you are behind, you're like, oh God, I really just want to understand machine learning. All the VODs are on YouTube. All the code and everything is on GitHub. So don't feel like if this is way past where your comfort level is with machine learning, that's because you're walking in on day 8. So, you know, make sure you check out the intro videos for like linear and logistic regression, because that'll really get you started. And Flycatcher14, thank you for following. All right, so we've got our random weights. We got a good shape that we're looking at. All right. Okay. All right, neural net Ned. Oh. Outputs. I forgot to rename something. Because it's called output. Oof. I told you it wasn't going to be pretty. I warned you. I'm not sure you were ready for it. It ain't so great. We weren't really expecting it to be great. But still, it kind of hurts, doesn't it? All right. So now that we've trained and we're a hot mess, let's see how our hot mess does. Come on, neural net Ned. I love this. I love how bad it is. It makes me so happy. All right. Oh, I haven't written the predict function yet, haven't I? All right. Hold, please. So let's since we know we're so great, our neural net's doing excellent. Let's try to predict. And let's see. McChillin, he says, it's just a hobby that I do, or do I work? No, but this is my job. So not hanging out with fun people like you, of course, is not my job. And teaching it isn't my job. But building it is my job. I guess my title at work right now is lead machine learning developer. So, woohoo! We are going to let's do some predictions. I'm so excited for this. Let's see how our crappy neural net does. It's okay. It's like a little baby. It's just trying. It's trying to learn. It doesn't know how bad it is. All right. And Tadas V123 asks, what did I study in school? For undergrad, I studied North African linguistics and philosophy. And in graduate school, I studied astrophysics. And Macroche, you say, what am I referring to while building? I have my notes over here because before every stream, like today I spent hours, honestly. I spent stream started, actually I had to push stream by 30 minutes. So I spent about 4+ hours writing all the notes, structuring the content so that it made sense, like coming up with ideas for like metaphors, practicing drawing neural nets, and coming up with the code, testing the code, finding data that would work, cleaning it, all of that. So I have all of my notes next to me so that if, I answer a question from chat or something, or, I would rather, especially for prepared streams like this, these aren't my casual streams, I want to make sure I'm showing you stuff that works so that you can learn from it, versus me like having a typo somewhere and we spend 40 minutes hunting down the typo. So for the smoothness of stream, I make sure everything runs beforehand. And Daniel Alberto, thank you for following. Okay. Did I do it again? Of course I did. Forgetting all my methods. Do I have to probably have to It's gonna still be a poop. All right, neural net Ned, we're gonna rename you. This is gonna be neural net Steve. Gotta love instantiating objects. All right, neural net Steve. No, it's still pooping. It does have something called predict. Did I goof the, yep. Frickin' Jupyter notebooks. That's our problem. Name outputs is not defined. Where did I forget to? Oh my God, me with the S's. Just want everything to be an S. I literally want it to be outputs so bad when I named it. There we go. All right. Neural net Steve. Neural net Steve sucks butt. Look at this. All right, got this one right. All right, he's not actually doing so bad. Not the greatest. I would not use neural net Steve to, predict who's going to survive a horrible disaster. But it runs, which for our first neural net isn't bad. It's not bad. Not bad at all. So, recapping the things that we've done tonight. We have figured out what neural net structures, what the architecture looks like. We've figured out how neural nets process their inputs. We've figured out what activation functions are, what they look like, and one possible activation function that's used, which is our sigmoid function from logistic regression. We've figured out what a feed-forward pass through a network looks like. We've figured out what backpropagation looks like. We've also learned how neural nets get trained. And we've talked about the math of gradient descent a little bit and the math of backpropagation. We did do a stream on Titanic data earlier. So we did. Splecht, thank you. And Sylvan Mats, thank you for following. In any case, questions. So this is hopefully now, if we go back to our notes briefly, let's zoom out. This is, even if you don't remember the details, I want you to feel comfortable with, where's our term list? Thought I wrote them somewhere. Where did I write the list of things? In any case, I can do it off the top of my head. You should feel comfortable with weights, biases, neurons, layers. Yes, here we go, terminology. What our biases are, how training works, how does it all feel? Hi, Justice Good Joe. Oh no, you're coming in at the end. It's good to see you. So, MH Zenerman, that's our bias, remember? So, in this case, I used, oh, no, you mean the prediction, I'm sorry. So I did above 0.5. And Smash 8 Tap, thank you for following. I'm so glad, Justice Good Joe, and I'm glad you're here. I think it's been a fun stream. It's been a good one. So, but yeah, this has been a lot, though. Just like with the reinforcement learning stream, I know this has been a lot. We've talked about, I mean, geez. We've been talking about neural nets for 4 hours, so please feel free to speak up with questions. And let me see here. While you're all thinking of your questions, thinking of the things you don't know. There we go. Jay Closure, thank you so much for subscribing. Seriously, like, subscriptions mean so much because this is a hobby, like streaming is a hobby for me, and the support matters a lot because it helps me, like the tablet that allows me to write these beautiful notes. That was something bought by all of your subscriptions and your donations. So that means a lot. And you know, like it's helped a lot too because it can be draining a little bit streaming, especially when in the past, like, not a lot of people have watched, but having all of you here telling me, hey, this helps and you've learned something and you're going to subscribe because you want to support the channel and see more streams like this, that means so much. So thank you, Jay Closure. Thank you for the sub. And yes, all streams will be on YouTube. The code that we went through tonight will go up on GitHub. And then the Blackboard notes will go up on GitHub as well. Following the 12 days of machine learning miss, I'm going to write more detailed notes because my lecture notes, if you will, are much, much more detailed. They often have a lot of the math and everything. So if that is one of the things I'm hoping to do is to clean those up, have links for you, have images, stuff like that. But that will take a lot of time, given how much time it takes me to write the ugly, gross, sketched out versions for myself. It'll probably take a while to make those really beautiful notebooks. And make nice visualizations and things like that so that you can run them and learn from them. Those will be something once I'm done with all of the 12 days that I'll make available to you. Not Switch. We're not playing Switch. What am I doing? There we go. So here is, right, damn it, right. There is the schedule, and Sun1, thank you for following. So as you can see, we just wrapped up Neural Nets 101, and on Monday we're going to come back and do reinforcement learning part 2, kind of. So reinforcement learning part 1 we did on the 30th. That was really basic Q learning, or tabular Q learning. And then on Monday we'll come back, we'll apply a lot of what we've learned about neural nets to reinforcement learning and seeing how the two can do really cool things when we combine them. I will try, oh my god, the reinforcement learning stream I talked for 5 hours because reinforcement learning is just, it's really cool. So we'll see Monday how I'm doing. And then we've got some cool network analysis stuff. I want to do maybe social network analysis or show some graph theory. Natural language processing following that. And then we will wrap all of the wonderfulness up with some computer vision. And V Marquez H, thank you for following. So at the end of streams, I like to take a little bit of time to answer questions. If there are questions about machine learning as a field, data science, anything we've talked about in previous streams, it's just really nice to kind of smooth things out. Because I do know that as we're moving through the code and the notes and everything, I miss questions. So if there's things I've missed, or if you've got broader questions about AI, machine learning, anything in between, I would love to answer them while we kind of, let's see, Acromonic, you say, any good recommendations of deep learning books? Ooh. So the one that I was posting earlier, which, oh no, give me 1 second here. Where did I put it? There it is. This is a good introduction. I would say that once you get, like, once you're kind of, you feel comfortable with deep learning and you aren't necessarily, you're not kind of a beginner anymore, it's a lot of reading papers, at least for me. So once I understood and I learned all about like the architectures and the various different like approaches and things like that, I find that I more frequently find myself reading papers than reading a textbook. But let's see here. Apple II Games, yes, where do I train my models? So I am aiming to have everything for the 12 Days of Machine Learning Miss either be a pre-trained model, if it has to be, or being able to be trained locally, because I want this to be more accessible. Hi, Mare, thank you for following. Work stuff is different. All right. Deep learning books. Yay! I know just as good, Joe. I'm excited for graph theory too. I don't get enough chances to apply it at work, so that's been part of the fun of the 12 Days of Machine Learning Miss, is some of the models that I don't get a chance to build a lot for work that I've done more as side projects or just because I'm interested. It's fun to be able to have an excuse to talk all about them, build them with all of you, tell you all about them and how cool they are. And hi, Kumahuna, welcome. And Acromatic, you say, I've been using it already a bit, but research papers are too difficult at this moment. What is it about the research papers that are too difficult? I just added to Discord a papers channel so we can kind of almost like do a casual journal club, sort of. So if there are papers that you really want to understand in more depth, post them there. But I'd love to understand what it is about the papers that is holding you up, because I can also, make that a focus of future streams. And Acromatic, okay, the math, good. Well, Math Mondays are in the works, my friend. So stay tuned. Honestly, though, I mean, I understand the math, and even I honestly will struggle frequently with papers, because people seem to think that if they're written densely, that means that they're like really smart, when I take the opposite philosophy, if it isn't already apparent. And so sometimes they're just written poorly, or they're so dense that I have to read like the same section a few times. I find that doing kind of the way that I've been teaching all of you, where even before you get to the math section, you kind of extract that conceptual process. That's a lot of times what I do, like, where did I throw it? Oh. So when I was working on, not that, where is it? When I was working on understanding some really, really complicated natural language processing models, Dark Link 701, thank you for following. And Maronetrest? I screwed that up, didn't I? Like, I literally did it conceptually first, drawing pictures of the architecture, writing literally like step 1, step 2, step 3, figuring out like, okay, this is what it does. Here's exactly, like, a lot of times that's what I do when I'm reading the papers myself, because before I even touch the math, like, I find that you can get to a place where you understand the math, but you don't understand the concepts. And that's not helpful at all. Like, you have to be able to explain both. So like here's a good example. Here's one where just literally, step by step, here's what you do. And that was a hefty paper. But that at least is my approach. So before you even touch the math, even if you're not ready for the math, if you can extract that conceptual approach, the step-by-step process that they're getting at, it can help you, it can kind of set you on the road to success. And 3D Prema, you ask how to combine astrophysics and biology in simulation. Ooh, that would be really, really cool. I know there's definitely a lot of chemistry done in planetary astronomy that would be probably very similar. And I've seen a lot of very interesting genetic algorithms used in contexts that are not at all biology. Red Chair Bird Hat, thank you for following. Astrobiology is an existing field. I've actually taken some classes in it. It's quite interesting. I will say that. It is very, very interesting. Hopefully in the future it will get even more interesting. Mateus FP, you say hi, greetings from Brazil. Hi, how are you? How are you doing? Also to help learn it all together. Yes, I mean, I would say that, you know, a lot of times when people are talking about successful machine learning, it really combines, the math, like the data processing and awareness, the models and everything, and also subject matter expertise. And so I would say you really do need that to have a highly informed model. Okay, so let's see here. And Sky, you say, no worries if you couldn't be here for the main body of the stream. It will be on YouTube. Also, I mean, the VOD will be up. I think it went well. I mean, you should probably ask everyone else, not me. I always think stream goes well. If I'm building machine learning with all of you and telling you all about cool math stuff, I feel like it's great. But you'll have to ask everyone else and see if it goes well. And let's see. V Marquez, thank you so much for subscribing. I really appreciate it. Hopefully I will see you in future Machine Learning Miss streams. Hopefully you'll be here for more either Math Mondays or even if it's just the rest of our 12 days of Machine Learning Miss. Let's see here. So, and Kumahuni, you ask, I'm curious how you study machine learning in relative topics. How do you mean? What do you, when you ask, and let's see. Evani Gosu, thank you for following. Some interactive that model also makes sense of the data process. Yeah, of course, Dieticus, you say thanks for the lesson. And so Kumahuni, so how do you study machine learning? I would say it depends on your background. And it really does, because if you feel really comfortable with math and statistics, you might be better off studying more of the programming side. If you're like a software developer or something, you might need the brush up on the math and the statistics. So it really depends on your background and what you're aiming to achieve with your machine learning education. There are definitely some great books, but different books require different backgrounds. So it's like, I hate to blanket recommend certain things without understanding kind of what a person's background is. And Guy Ross, thank you for following. Okay, so, it is almost midnight my time, and, we've had quite a hefty stream full of neural nets and wonderful goodness. And Ooj Tua, thank you for following. So we are going to raid now, but hopefully all of you will be back. And Ian Alex, I thank you for the bits. We will bank your bits. We are up to, I think, 5 treats for the dogs. Please try to stay around and, if I could spell this right, help me raid somebody who has raided me many times, smaller streamer. I'd love to pass forward some of this love. So if you don't mind sticking around. Oh, I could try feeding Hubble. All right, really quick, before the raid, who wants to feed my dog? Let's give my dog some treats. Let's see if I can get him to, oh, good boy. Let's see if he's gonna be a good boy. Hold on, we're gonna pull this up. Dogs are the best way to do all stream things. So, let's see. It is connecting. Hold, please. And thank you, Classed Ember. And if I didn't already say it, Kumahuna for stopping by. Thank you for following. It's loading. Give it a second. It's worth it. My dog's really cute. Come on, computer. Ugh. You would have to, I think, unplug and replug it in. Loafbone. Can you do that real quick? All right. While this is rebooting, because technology, you unplug it, you plug it back in. Castillo, thank you for following. Dogs are taking over the video world, and I think if dogs, take over the world, that would be a wonder. At least if my dog took over the world, it would be wonderful. We've actually we've had some interesting discussions about machine learning when machine learning is challenged by dogs. So very funny stories about the challenges of overfitting with machine learning, right? Because that's the whole point, unless we're talking reinforcement learning, right? Is to generalize the ability to do the tasks that we have talked about. Do I need chat data from machine learning streams? Why not? I don't know. Sure. I don't know what I would do with it. It's only like eight streams now, but what kind of chat data are you talking about? I don't want to like study my own data. Like I don't want to be like, oh man, when you told that funny story, everyone left. That'd make me very sad. So all right, I'm going to give the Furbo one more try. Yes. All right, friends, dog time. Are you ready? Look how freaking cute my dog is. All right. Okay, Hubble. Let's give Hubble some treats. Hubble's had a really rough day. Hubble has been at the vet for hours. Why is it being weird? What the hell, Furbo? Hold on. There we go. Come on, Furbo. How do I go back? Oh God. This, I think. Yes. Okay. His paw's doing better, Ian Alex Hart. Oh, there we go. Look at this cute little boy. Oh my God, why the four Hubbles? I don't know why it's doing this. But we'll give Hubble 4 treats. Lots of good Hubble here. He's very sleepy. He had a lot of vaccines today. I don't know why it's being weird. I actually don't know enough about Furbo. What's it now? Whatever. Just gonna keep flinging treats at him. Love me, dog. Love me. No, but he's a very, very good boy. He's had a rough day. He's been at the vet. And then there was a fire alarm, so he's had a bit of a harder day. So we'll give him one more treat, like a very good boy, and then we'll raid. Actually, while we're get this ready. Stick with me. Try to pass forward some love. This is somebody who has raided me very, very frequently, and I would love to be able to show some appreciation. So if you all can stick with me, let's give an awesome raid to my friend Non-Dairy Neutrino. And I will see you all on Monday. All right? Have a good night.